In the dim glow of late 17th century Europe, when scientific thought was still stitched together from fragments of ancient philosophy and the first sparks of modern mathematics, a quiet revolution took shape in the mind of a young scholar from Lincolnshire. The world around him moved according to rhythms that seemed both predictable and mysterious. Apples fell, moons circled, tides swelled, and planets traced wandering paths against the night sky. Scholars had described these motions for centuries, yet no single idea connected them. Nature felt like a puzzle scattered across time, waiting for a mind capable of assembling its pieces into a single image. Isaac Newton approached that puzzle with a blend of caution and bold imagination. By the year 1687, he completed a work that did not simply answer questions, but redefined the entire language used to ask them. In his Principia, he presented the law of universal gravitation, a rule that claimed every object in the cosmos attracted every other object. A stone on the ground reached invisibly toward the moon. The sun tugged on the planets. The planets pulled on one another. Everything in creation was entangled in a mutual dance of attraction. What made this idea astonishing was its simplicity and its reach. A single relationship applied both to a falling apple and to the orbit of the moon. Newton expressed this attraction as a force acting across empty space. Two masses separated by distance influenced each other instantly. The universe could be imagined as a grand mechanical stage where bodies moved according to precise mathematical relationships. Kepler's elegant laws describing planetary motion suddenly gained deeper meaning. The elliptical paths of Earth and Mars, the rapid swing of Mercury around the Sun, and the long sweeping arcs of comets all emerged naturally from Newton's equations. For the first time, scientists possessed not only descriptions, but explanations. Astronomy entered an age of precision. Observers charted the heavens with confidence because they trusted the mathematics guiding their predictions. When the orbit of Uranus drifted slightly from expectation, astronomers did not suspect Newton's law. Instead, they suspected an unseen planet disturbing the motion. With nothing but Newton's mathematics and careful observation, they calculated where this hidden world should be. When telescopes finally revealed Neptune near the predicted position, the success was so dramatic that Newton's theory seemed beyond challenge. It appeared that the universe had confessed its deepest secret, and had done so in the language Newton provided. Yet behind this success lingered an unsettling question. How could one object exert influence across empty space without any medium in between? Newton himself admitted discomfort with this idea. He did not claim to understand the mechanism. The mathematics worked, and that was enough to describe the phenomena, but there was no physical explanation for the connection. In his time, there was no known alternative, so the mystery remained untouched. As the centuries progressed, the cracks became slightly more visible. During the 19th century, an entirely different picture of nature emerged from the study of electricity and magnetism. The work of Faraday and Maxwell showed that electromagnetic waves traveled at a specific speed through space. This discovery raised a troubling implication. If light required time to pass from one place to another, could gravity truly act instantaneously? The two ideas did not fit comfortably together. Newtonian gravity ignored distance and delay, while electromagnetic waves respected a firm, universal speed limit. Astronomers uncovered another small inconsistency. The path of Mercury shifted in a way that could not be accounted for fully by Newton's predictions. Most of this shift resulted from gravitational influences of other planets, but a tiny remainder continued to resist explanation. This leftover amount was measured with growing accuracy as instruments improved. Though the discrepancy was small, its persistence signaled that the Newtonian picture might not be complete. Still, Newton's framework remained unmatched in its usefulness. It guided the expansion of celestial maps, shaped early geodesic measurements on Earth, and supported navigators who crossed oceans by charting the stars. The theory worked so well across so many domains that few doubted its fundamental correctness. To challenge it required not just new mathematics, but a new way of imagining space and time themselves. By the late 19th century, nature began offering hints that deeper truths waited beneath the surface. The behavior of light conflicted with Newtonian expectations. The structure of electromagnetic fields suggested that space possessed properties not captured by classical physics. Small anomalies in planetary motion raised stubborn questions. These clues did not topple Newton's theory, but they nudged scientists toward the realization that the familiar picture of gravity as a simple force might conceal a more intricate reality. As the 20th century approached, physics stood at a crossroads. The old framework remained powerful yet incomplete. Something subtle was wrong, and the universe was quietly insisting that a new idea was required. This is where the story begins to turn, not with the fall of Newton's brilliance, but with the rise of a deeper understanding that would reveal the fabric of space and the flow of time as the true architects of motion. The shift that awaited physics did not arrive with thunder, but with a quiet rearrangement of ideas that had long been taken for granted. As the 19th century yielded to the 20th, careful experiments kept revealing that the universe did not honor the absolute space and absolute time assumed in the Newtonian world. Light did not change its speed depending on the motion of the observer. Measurements of electromagnetic fields showed that nature insisted on a fixed value for the speed of light, a value that did not bend to convenience or expectation. This stubborn constancy created a tension that mathematics could not ignore and observation could not dismiss. Scientists expected that light should move differently depending on the motion of Earth through space. They imagined an invisible medium surrounding the planet, something like a cosmic sea in which light waves rippled outward. If Earth drifted through this medium, the speed of those ripples should shift. Yet experiment after experiment showed no such change. The Michelson-Morley experiment in the year 1887 produced a result that seemed impossible at the time. No matter how the apparatus turned or how the experimenters adjusted their measurements, the speed of light refused to alter. Nature maintained a rigid silence regarding any underlying medium. Mathematicians like Lorentz tried to preserve the Newtonian framework by adjusting the equations that described motion. They introduced transformations that allowed objects in motion to behave as though the speed of light remained unchanged. These transformations were clever corrections, patches meant to fit new observations into an old picture. What no one yet realized was that these adjustments were not temporary fixes. They were the outlines of a new geometry, a shape of experience that would soon replace the familiar one. Meanwhile, the growing precision of astronomical observations kept whispering that Newton's law, though powerful, did not fully describe the solar system. Mercury continued to trace its slightly mismatched path around the Sun. The displacement was tiny, so small that earlier generations could overlook it, but better instruments made it impossible to hide. Astronomers corrected for every known influence of the other planets. They refined their calculations again and again. Still, the orbit failed to match prediction. This mismatch did not announce itself boldly. It crept into the margins of observation, persistent and patient, waiting for a mind capable of understanding its meaning. In laboratories across Europe, physicists studied the behavior of moving charges and the patterns created by oscillating electromagnetic fields. These patterns did not obey Newton's laws in any simple way. They hinted that time flowed differently when objects moved quickly, that lengths contracted, and that clocks shifted their rhythms. None of this aligned with the classical image of a universal stage where events unfolded on a single shared timeline. The data suggested that the stage itself might stretch or compress depending on motion, altering the performance in ways Newton never imagined. As these clues accumulated, a sense of unease settled over the scientific world. Newton's theory still predicted planetary motions with remarkable accuracy. It still described tides, projectiles, and celestial mechanics with near-perfect reliability. Yet nature was pushing back gently, revealing cracks that could not be smoothed over indefinitely. The conflict between the behavior of light and the assumptions of classical physics grew sharper each year. The elegant curve of Mercury's orbit continued to whisper that gravity might not be a force in the way Newton conceived it. Physicists who studied the foundations of mechanics began to realize that the issue was not simply the law of gravity, but the deeper assumptions about space and time themselves. They had been treated as separate and absolute. Time advanced uniformly for all observers. Space stretched out as a rigid backdrop. But experiments showed that this picture could not hold. If light remained constant for all observers, then space and time would have to adjust to protect that constancy. They were not fixed. They were dynamic, and their behavior shaped the movement of matter. In the midst of this quiet crisis, a young patent clerk in Bern studied these contradictions not as isolated puzzles, but as reflections of a deeper structure waiting to be revealed. He would reimagine motion without assuming an absolute frame. He would show that simultaneity was not universal. He would argue that time could slow under certain conditions and that lengths could contract. His ideas would not be patches or corrections. They would form an entirely new architecture for reality. But in this moment, at the dawn of the 20th century, before his discovery took shape, the scientific world lingered in a rare state of anticipation. The equations that had guided astronomy for centuries were no longer sufficient. The behavior of light challenged the foundations of classical thought. Space and time, once believed to be the unchanging backdrop of existence, were starting to shift beneath the disciplined gaze of experiment. The universe was preparing to reveal that gravity was not a force reaching across distance, but the expression of something deeper, something woven into the very structure of reality. A transformation was approaching, and the next insight would come not from centuries of tradition, but from a mind willing to accept that the familiar world might be only a shadow of a more profound design. The 20th century opened with a quiet sense that something fundamental had been overlooked in the classical picture of nature. Astronomers continued to chart the skies with the confidence built on Newton's equations, yet their instruments kept uncovering hints that the cosmos was more intricate than the simple pull of masses across empty space. Physicists studying light and electromagnetism found themselves confronting a universe that refused to bend to assumptions once held sacred. These two worlds, the astronomical and the experimental, were drifting toward a shared conclusion. The Newtonian vision, though magnificent, was incomplete. It was not the failures that drew attention. Newton's theory excelled at describing the motions of planets and the rise and fall of tides. It guided explorers across oceans and helped engineers build early machines that obeyed classical mechanics flawlessly. But nature does not measure theories by their beauty or their legacy. It reveals its truths through small inconsistencies that remain when everything else fits neatly into place. Mercury's subtle orbital discrepancy persisted through every improvement in observation. The unwavering speed of light challenged every classical assumption about velocity addition. These details behaved like threads dangling from a tapestry, inviting the curious to pull them and reveal a deeper pattern. Scientists attempted to preserve the familiar picture by adjusting small pieces rather than rethinking the whole. They invented hypothetical mediums for light, introduced correction factors, and searched for undiscovered planets that might explain Mercury's orbit. But the puzzles did not vanish. Instead, they pointed in a consistent direction toward an idea so radical that it required the rewriting of notions held for centuries. The errors were too systematic and too closely tied to the behavior of light and motion to be accidents. Something in the structure of space and time themselves had to give way. In this atmosphere of uncertainty, the study of motion grew more precise. Faster objects did not appear to obey the same timing as slower ones. Experiments showed that electric and magnetic fields transformed into one another depending on the motion of the observer, suggesting that nature did not treat space and time as rigid and separate. The equations that describe these transformations hinted at a new geometry beneath everyday experience. They whispered that events that seemed simultaneous to one observer might not be simultaneous to another. They suggested that clocks could tick at different rates depending on speed. These ideas were difficult to imagine, but impossible to ignore. Yet even as these discoveries emerged, gravity itself remained tied to the older view. It was still seen as a force acting instantly between masses. A picture that did not mesh with the growing evidence that nothing in the universe moved faster than light. The instant action postulated by Newton could not survive in a world where information required time to travel. If the sun were to vanish, Newtonian gravity implied that Earth would feel the change immediately. But experiments in electromagnetism made it clear that disturbances in fields propagated at the speed of light, not infinitely fast. The need for a new framework became unavoidable. The scientific community approached this turning point cautiously. Overturning a theory as successful as Newton's required undeniable evidence and a conceptual framework strong enough to replace it. The pieces of that framework were scattered across decades of research in optics, electromagnetism, and mechanics. But no one had yet gathered them into a unified picture. Instead, the world waited for someone who could recognize that the contradictions were not flaws in isolated experiments, but windows into a new understanding of reality. As the 19th century faded, the stage was set for a transformation that would shift the meaning of gravity, motion, and even time. A young thinker, working far outside the traditional halls of academia, would soon demonstrate that space and time were not the silent background of the universe, but active participants in the dance of matter and energy. He would show that clocks could slow, rulers could contract, and that the familiar experience of gravity was merely the shadow cast by a deeper geometry. But here in the final years before that revelation, the universe still appeared divided between two truths. One truth came from Newton, a majestic and dependable description of the celestial clockwork. The other came from light, a stubborn messenger refusing to behave according to classical expectations. Between them lay the first faint outline of a new world. A world in which mass and motion sculpt the very shape of time, and where gravity itself would soon be understood not as a pull, but as a path carved by the curvature of space-time. This moment is where the story stands poised on the threshold of transformation. The clues have accumulated, the inconsistencies have sharpened, nature has spoken quietly but firmly. And the next step will come from a mind ready to accept that reality is stranger and deeper than the classical world ever imagined. At the dawn of the 20th century, the world of physics found itself caught between two incompatible truths. One truth came from the classical picture that had guided science for centuries. Space was an empty stage. Time flowed with steady rhythm for all observers. Gravity acted as a force that stretched across distance without delay. The other truth came from the stubborn behavior of light and electricity. Light refused to change its speed no matter how observers moved. Electric and magnetic fields transformed into one another as though space and time were woven into a single fabric. These two visions could not coexist, yet both were supported by precise measurements. Nature was quietly insisting that something fundamental had been misunderstood. The turning point did not come from dramatic failures, but from small contradictions that refused to disappear. Experiments showed that the speed of light remained constant, even when measured on a spinning Earth racing around the sun. This constancy defied classical expectations. If a person walked inside a moving train, their speed relative to the ground changed. Why did light not behave the same way? Scientists expected that Earth's motion would cause a slight difference in the speed of light measured in different directions. Instead, the Michelson-Morley experiment revealed no such difference. The light rays returned to their detectors with perfect balance, as though the universe cared nothing for Earth's movement. This result forced a re-evaluation of ideas once considered unshakable. Physicists attempted to salvage the classical framework by proposing an unseen medium through which light traveled. This imaginary substance was meant to act as the stage for electromagnetic waves, but experiment after experiment failed to reveal its presence. The medium behaved like a ghost that influenced nothing, resisted nothing, and affected nothing. It served no role except to preserve a familiar worldview. Eventually, the silence of nature made clear that such a medium did not exist. Light did not need a substance to carry it. It moved through the structure of space itself. Meanwhile, a different set of clues emerged from the study of motion and electricity. When charges moved at high speeds, their behavior changed in ways that classical mechanics could not predict. Magnetic fields appeared to arise from electric fields depending on the observer's motion. These transformations were captured in mathematical relationships called Lorentz transformations, which were created to protect the constancy of light. These transformations altered the understanding of length and time. According to them, moving rods shortened and moving clocks ticked more slowly compared with those at rest. This idea sounded impossible, yet the mathematics aligned perfectly with experiments. Even more unsettling was the realization that simultaneity was not universal. Two events that seemed to happen at the same moment for one observer might not be simultaneous for another observer moving at a different speed. This shattered the long-held assumption that time was absolute. If time could not be shared across observers, then the Newtonian world picture began to dissolve. The universe was hinting that space and time were not separate entities, but strands of one interconnected reality. These hints would soon lead to a profound reimagining of motion itself. The growing conflict between classical expectations and experimental evidence placed physics on uncertain ground. The behavior of light refused to bend. The mathematics of electromagnetism pointed to an underlying unity of space and time. And the orbital motion of Mercury continued to reveal a small discrepancy that would not disappear. Each clue seemed to push the scientific world toward a new perspective, yet no one had yet taken the final step of rewriting the foundations of motion. In this atmosphere of confusion and possibility, a young thinker examined these contradictions with unusual clarity. Rather than adjusting equations to preserve the old worldview, he questioned the assumptions that had shaped physics since the time of Newton. He asked whether time itself might change depending on motion. He wondered if space could stretch or compress. He considered whether the speed of light was not merely a property of waves, but a fundamental feature of the structure of reality. This approach transformed the contradictions into a coherent picture. But before that picture emerged, the scientific world found itself suspended between certainty and discovery. The classical framework had guided centuries of progress, yet it no longer matched the precision of modern experiments. The behavior of light demanded that space and time be reimagined. The stage was set for a theory that would unite these fragments into a single vision, one that would reshape the meaning of gravity itself. The strange behavior of light continued to press against the edges of classical understanding, urging scientists to confront the possibility that the universe was built on principles far different from what their intuition suggested. As researchers studied the equations of electromagnetism, they noticed that these equations contained an inherent structure that did not allow the speed of light to vary. The speed emerged naturally from the relationships between electric and magnetic fields, not from any physical medium. This meant that the constancy of light was not an accident, but a fundamental property of the universe. If the speed of light remained unchanged for all observers, then something else had to change. Space and time themselves would need to shift to protect that constancy. Physicists wrestled with this implication. They tried to imagine mechanisms that could shield the classical worldview from collapse. Some suggested that objects physically contracted when they moved through the imagined light-carrying medium. Others proposed that moving clocks slowed because of interactions with that medium. But these explanations required invisible processes that operated without detectable effects. They served only to preserve the older conception of absolute space and absolute time. As experimental precision increased, it became clear that such explanations strained credibility rather than enhancing understanding. The Lorentz transformations, originally devised as mathematical adjustments, hinted at a deeper truth. These relationships declared that measurements of length and time depended on the motion of the observer. A clock in motion would tick more slowly compared with a stationary one. A moving ruler would appear shorter along the direction of its motion. Most astonishing of all, two observers moving relative to each other would not agree on whether two distant events occurred at the same moment. The familiar idea of simultaneity dissolved into a concept dependent entirely on perspective. Nature was revealing that time was not universal. It flowed differently depending on the state of motion. These revelations unsettled the scientific community because they struck at the very foundation of Newtonian physics. Newton had built his theory on the idea that time was absolute. Every event in the universe could be placed on a single shared timeline. Every observer experienced the same passage of time regardless of their motion. Space, similarly, was treated as a rigid and unchanging arena. But the emerging evidence showed that neither of these assumptions held true. If space could stretch or contract, and if time could flow at different rates for different observers, then the classical picture of forces acting across a fixed stage could not survive. The tension between observation and tradition reached a breaking point as the behavior of fast-moving particles became increasingly important in physics. Experiments using charged particles demonstrated effects that could not be explained by Newtonian mechanics alone. These measurements aligned perfectly with the predictions made by the Lorentz transformations. The more carefully scientists measured the world, the more clearly they saw that the classical assumptions were failing. Every new experiment confirmed that the structure of reality was far more flexible than once imagined. Meanwhile, the mystery of Mercury's orbit added weight to the growing sense that gravity required a new description. The slight mismatch in the rotation of Mercury's elliptical path around the Sun resisted every classical correction. No hidden planet could explain it. No known gravitational influence accounted for it. Observers tracked the planet with increasing accuracy, calculating its motion with careful precision. The stubborn remainder of its precession stood untouched, a quiet signal that an unknown influence shaped its path. All these clues pointed in a single direction. The universe required a framework where space and time were not fixed but dynamic, capable of bending and stretching. A framework where the motion of observers influenced their experience of time. A framework where the speed of light was not merely the speed of a wave, but a fundamental constant that anchored the structure of space-time itself. The scientific world was poised for a conceptual leap, though few recognized it at the time. Many scientists believed that the classical theory needed only minor corrections. They could not yet imagine a universe where time itself could dilate or where rulers could contract. They could not imagine a reality where gravity was not a force, but a consequence of geometry. Yet these ideas were already embedded in the mathematics that described electromagnetism. They waited only for someone to see the pattern clearly. Into this landscape stepped a young thinker prepared to question what others took for granted. He approached the contradictions not as problems to be patched, but as clues pointing toward a deeper unity. Instead of insisting that space and time remain fixed, he allowed them to change. Instead of assuming that forces acted across empty space, he wondered whether the structure of space itself guided motion. By accepting the constancy of light as a fact rather than an inconvenience, he opened the door to a new understanding of reality. The world was about to learn that the collapse of the old framework was not a loss, but the doorway to a richer, more accurate picture of the universe. The pieces were ready. The evidence was clear, and the next insight would transform not only physics, but the way humanity understood space, time, and gravity. The scientific world stood in a quiet tension as the 19th century faded into the 20th, as though nature were holding its breath before revealing a truth it had been hinting at for decades. The evidence sat plainly in laboratories and observatories, yet its meaning remained just out of reach. Light moved with unwavering speed, no matter how Earth rushed through space. Clocks and lengths appeared to behave differently at high velocities. Electromagnetic fields seemed woven together in a way that demanded a deeper unity of space and time. And the path of Mercury continued its slow defiance of classical prediction. Each piece formed a pattern, but only a mind willing to loosen the grip of old assumptions could see the full shape emerging. Scientists clung to the belief that time flowed uniformly for all observers because it felt inseparable from human experience. Days passed with predictable rhythm. Clocks ticked steadily. The flow of seconds appeared universal. To imagine otherwise required setting aside intuition and trusting the subtle hints embedded in nature's behavior. Yet experiment after experiment whispered that time was not as rigid as it appeared. If the speed of light truly remained constant for all observers, then something else had to shift to maintain that balance. That something was time itself. As researchers examined the Lorentz transformations more carefully, they began to see a strange but undeniable symmetry. These equations suggested that motion altered measurements of both space and time in precisely the way needed to preserve the speed of light. No matter how fast an observer moved, light would always outpace them, not because light changed, but because the observer's own measurement of space and time changed. This was not a trick of mathematics. It was a reflection of a deeper structure forming the backbone of physical law. Still, the idea clashed with centuries of understanding. If time could slow and distances could contract, then the world was not Euclidean in the simple classical sense. It was more fluid, more dynamic, shaped by relationships rather than absolutes. Many physicists hesitated to abandon the familiar world. They preferred explanations that preserved classical intuition, even when those explanations required contrived adjustments. But the more experiments they performed, the clearer it became that the classical world was only an approximation, useful but incomplete. The contradiction between Newtonian gravity and the behavior of light sharpened the need for a transformation. In the Newtonian view, gravity acted instantly across any distance. If the sun were to shift slightly, Earth would feel the change immediately. But electromagnetic disturbances took time to travel, and the speed of light set a universal limit. It made little sense for the universe to allow information about gravity to propagate infinitely fast, while every other influence respected a cosmic speed cap. The mismatch between these two pictures had grown too large to ignore. Astronomers watching Mercury's orbit recognized that this tiny anomaly was not merely a curiosity. It was a message. The solar system was revealing that the Newtonian framework could not describe reality with perfect precision. The small deviation persisted across decades of increasingly accurate observations. Every time Mercury swung around the Sun, it carried with it another confirmation that something deeper shaped the paths of planets. The gravitational pull described by Newton was powerful but not complete. The growing web of evidence created a sense that physics approached a turning point. The contradictions were too intertwined to be resolved by local adjustments. They pointed toward a single idea waiting to be articulated, a new conception of space and time capable of harmonizing light, motion, and gravity. Nature had already laid the foundation. It waited only for someone willing to break from centuries of tradition and see space and time not as the fixed stage of events, but as participants in the unfolding of motion. At this moment, a young thinker began to examine these problems with uncommon clarity. Working outside the prestige of established academic institutions, he approached the contradictions without the weight of convention. He did not begin by trying to preserve the classical worldview. He began by accepting the experimental facts exactly as they were. The speed of light was constant. Time could vary with motion. Space could shift in response. From these ingredients, he would craft a new picture, one that dissolved the contradictions and revealed a deeper unity binding all phenomena. Before the world recognized his work, the scientific landscape felt unsettled, perched on the edge of discovery. Every experiment nudged it closer to the inevitable conclusion that the Newtonian picture was only a shadow of a richer reality. Space and time were preparing to reveal themselves as a single geometric structure, flexible and dynamic. Gravity was preparing to shed its identity as an invisible force and emerge instead as the curvature of that structure. The stage was set. The tools were ready. The clues had aligned into a pattern that only needed a mind bold enough to read it. And soon, the world would witness the arrival of a theory that would rewrite the meaning of motion, unify the behavior of light with the structure of space and time, and resolve the ancient questions that Newton himself had left unanswered. The world did not immediately recognize the magnitude of the shift that was about to unfold. In the early years of the 20th century, a young clerk sat at a worn desk in the Byrne-Paton office, reading through technical documents and mechanical proposals while the quiet hum of routine filled the room. Outside that small office, Europe moved through ordinary days, unaware that the foundations of physics were preparing to tilt. Inside that office, a mind was assembling the fragments of a new reality from clues that others had treated as isolated curiosities. Instead of patching the old framework, he allowed himself to imagine that space and time could behave in ways no one had dared to consider. Albert Einstein approached the contradictions troubling physics with a rare willingness to trust the evidence over the comfort of tradition. He accepted without hesitation that the speed of light remained constant for all observers because experiment demanded it. He accepted that simultaneity might not be universal because the mathematics of electromagnetism pointed toward that conclusion. And he accepted that the concept of absolute time might be an illusion, not because he wished to challenge Newton, but because nature itself refused to cooperate with the Newtonian picture. His genius lay not in rejecting the old worldview aggressively, but in allowing himself to explore the consequences of the clues that others considered puzzling. Einstein asked a question both simple and revolutionary. What if the laws of physics were identical for all observers moving at constant speed? And what if the speed of light was the same for everyone regardless of their motion? These two statements, both grounded in experimental evidence, formed the heart of his reasoning. From them, he followed the logic with unwavering discipline. If the speed of light could not change, then space and time must adapt. Distances must stretch or compress depending on motion. Clocks must tick at different rates. Events that seem simultaneous for one observer might not be simultaneous for another. The universe must be built not from separate absolutes, but from an interconnected fabric that responded smoothly to changes in motion. This reasoning led to a picture so unfamiliar that even Einstein paused to consider its implications. Yet he trusted the mathematics and the evidence. He showed that time dilation was not a theoretical trick, but a natural result of preserving the speed of light. He demonstrated that lengths contracted along the direction of motion because space itself adjusted to maintain consistency with the behavior of light. These effects were small at everyday speeds, but became unmistakable as objects moved faster. The classical world of absolute time and rigid space could not survive such transformations. The universe required a deeper structure. Einstein understood that these ideas were unsettling, not because they were complicated, but because they contradicted centuries of intuition. Human experience did not reveal time stretching or clocks slowing. But human experience also did not reveal the speed of light or the behavior of electrons in motion. Nature held realities far beyond the reach of everyday perception. Special relativity, completed in the year 1905, was Einstein's answer to the contradictions between classical mechanics and electromagnetism. It revealed that space and time formed a single unity, a four-dimensional stage where events unfolded according to geometric relationships that shaped the motion of matter and light. The most profound result of this new picture emerged not from the behavior of motion, but from the relationship between energy and mass. Einstein demonstrated that mass carried energy and energy possessed mass-like properties. This relationship, expressed in the now famous equation linking mass and energy, hinted that gravity might not be a simple force acting across distance. If mass and energy shaped the behavior of objects and also influenced one another, then the nature of gravity likely went deeper than the pull described by Newton. Special relativity made clear that the classical idea of instantaneous forces acting across space could not survive in a universe where light set a universal speed limit. Einstein recognized that if time could slow and space could stretch depending on motion, then gravity could not remain a force acting across an unchanging background. He needed a new principle to guide him toward a deeper understanding. That principle arose from an insight so simple that it seemed almost too elegant to hold the seeds of a revolution. He realized that a freely falling observer, someone in complete weightlessness, would feel no gravity at all. Standing inside a sealed elevator in free fall, a person would float as though gravity had vanished. This meant that locally, in small regions of space and time, there was no distinction between free fall and weightlessness. Gravity could disappear entirely if one adopted the right frame of motion. This thought, gentle yet profound, became the cornerstone of a new era. Einstein recognized that if gravity could be erased by choosing an appropriate frame, then perhaps gravity was not a force in the usual sense. Perhaps it was a reflection of the way space and time themselves behaved. If motion could reshape the flow of time, then mass and energy might reshape that flow as well. The idea pointed toward geometry rather than force, toward curvature rather than pull. Einstein had begun rewriting the meaning of reality with nothing more than careful reasoning and the courage to accept what nature had already shown. The next step would require reimagining gravity from the ground up. It would require tools from mathematics that described curved surfaces and distorted spaces. It would require a leap from familiar three-dimensional intuition to a four-dimensional universe shaped by energy and motion. And it would require the conviction that gravity was not an invisible tether pulling on objects, but a manifestation of how time itself flowed through the universe. The path ahead would be long and challenging, but Einstein had found the key that would unlock an entirely new vision of gravity, one that would replace centuries of thought with a single insight. He had shown that the universe did not operate under the tyranny of absolute time. Time could bend, time could stretch, and through this flexibility, the very structure of reality would reveal its hidden architecture. Einstein carried his insight with quiet determination, sensing that the path forward required more than adjusting equations or repairing inconsistencies. He felt that gravity itself needed to be rebuilt from the foundations. If a falling observer could erase all sense of weight, then gravity could not be an ordinary force. It had to emerge from something deeper, something woven into the behavior of space and time. This realization pressed him to search for a new language, one capable of describing motion, not on a flat and rigid stage, but on a surface that could curve, stretch, and reshape itself in response to mass and energy. He understood that the familiar picture of forces acting across distance no longer fit a universe in which the speed of light set an absolute limit on how information traveled. If gravity acted instantly, it violated the structure revealed by electromagnetism. If gravity acted with delay, then the Newtonian picture fell apart. The solution had to be a model where gravity was not transmitted at all in the traditional sense. Instead, gravity needed to arise naturally from the shape of the universe. Objects should move not because they were pulled by unseen forces, but because they followed the straightest possible paths through a geometry influenced by mass and energy. To explore this idea, Einstein studied the mathematical work of Bernhard Riemann, the 19th century thinker who introduced a new way of describing curved surfaces. Riemann's mathematics explained how a surface, like a sphere or a saddle, could possess its own geometry independent of the space surrounding it. Distances, angles, and paths all behaved differently depending on the curvature. Einstein saw that these tools might hold the key to understanding how space and time could curve in the presence of mass. If the geometry of space-time changed near massive objects, then the paths that planets followed could be understood not as orbits carved by invisible forces, but as natural motions within a curved four-dimensional landscape. This perspective required reimagining even simple experiences. Consider a marble rolling across a stretched sheet. If the sheet dips, the marble changes direction not because a force tugs on it, but because the shape of the surface guides its motion. Einstein realized that this simple analogy hinted at something profound. Gravity might be nothing more than the curvature of space-time caused by mass and energy. Objects such as planets and stars do not feel a pull. They simply follow the shape of time and space around them. Their paths bend because space-time itself is bent. Einstein recognized that to express this idea with precision, he needed mathematical tools far beyond those used in classical mechanics. He began long and intense collaborations with friends and colleagues, including Marcel Grossmann, who introduced him to the advanced geometry needed to describe curved spaces in full generality. Einstein spent years wrestling with these concepts, often making progress only to realize that his equations failed to match the physical requirements. He pushed forward anyway, guided by intuition and an unshakable belief that nature must be internally consistent. During these years, he encountered repeated setbacks. He tested equations that seemed promising only to learn that they could not accurately describe the motion of planets or the behavior of light near massive objects. He tried formulations that preserved some aspects of Newtonian gravity, but discovered they were incompatible with the principles of relativity. Yet each failure refined his understanding. Every abandoned equation revealed something about the shape the final theory needed to take. The idea that mass could influence the structure of time itself became central to his reasoning. If time flowed differently at different locations, then the motion of objects would naturally shift in ways that appeared gravitational. For example, a clock closer to a massive object would tick more slowly than a clock farther away. This difference in the flow of time would guide the motion of objects without requiring any direct force. In this vision, the universe became a dynamic fabric, one that responded to mass and energy by bending and stretching. Einstein realized that if he could express this relationship mathematically, he would have a complete theory of gravity. But the mathematics demanded more than creativity. It required precision, discipline, and a deep understanding of how geometry and physics intertwined. Riemann's geometry provided the language, the insights of Lorentz provided the structure, the constancy of light provided the anchor, and Einstein's relentless dedication provided the direction. As the shapes and patterns of this new picture grew clearer, he sensed that he was approaching a moment where gravity would no longer appear as a mysterious force acting across empty space. It would instead emerge as a natural consequence of the way space-time curved in response to mass. The simple fact that a freely falling observer felt weightless became the doorway to a universe where geometry replaced force. But he still needed to find the final equations that defined this curvature in full generality. Einstein continued to refine the mathematics, inching closer with every attempt. He felt that nature was revealing its structure slowly, allowing him to test ideas until the correct pattern emerged. The world around him remained unaware that its understanding of reality was being transformed in quiet evenings and long walks through Bern. Space and time were becoming something dynamic, something alive, something capable of shaping the motion of every planet and every ray of light. The final form of this insight would soon reveal itself, but first, Einstein needed to express the relationship between mass, energy, and curvature in a way that captured the full depth of the universe's architecture. He was close, but the step from insight to equation would require one more leap, one more synthesis of geometry and physics. Einstein pushed deeper into the mathematics that would uncover the hidden shape of the universe. Each new attempt brought him closer to the realization that gravity was not a pull, but a feature of geometry itself. Yet the mathematics of curved spacetime was demanding. Einstein felt as though he were trying to read the blueprint of the cosmos through a fog that lifted only slowly, revealing fragments of structure before hiding them again. Still, he pressed forward, guided by intuition and by the unyielding constraints of experimental truth. He understood that any correct theory of gravity had to meet several strict requirements. It had to reduce to Newton's familiar law under ordinary conditions, so that the successful predictions of classical physics would remain intact. It had to preserve the principles of relativity by ensuring that no influence traveled faster than light. It needed to describe the motion of objects as paths through spacetime rather than responses to a force acting across distance. And most importantly, it had to explain the stubborn discrepancy in the orbit of Mercury, the small shift that classical physics could not fully capture. Einstein knew that if he could produce equations that satisfied all these conditions, he would uncover the true nature of gravity. As he worked through the geometry with the help of Marcel Grossmann and the ideas of Riemann, he slowly began to see the shape of a larger framework. Spacetime was not a static grid, but a flexible structure that mass and energy could curve. In this picture, the straightest path through spacetime, known as a geodesic, could appear curved when viewed from within three-dimensional space. Planets moved along these geodesics naturally, not because they were pulled by a force, but because spacetime guided their motion. A planet orbiting a star was like a bead sliding along the contour of a warped surface, following the shape without needing any external influence. Einstein sensed that this idea held the power to explain all gravitational phenomena. But he still needed to express it in a precise mathematical relationship, linking the curvature of spacetime to the mass and energy within it. He searched for an equation that could capture the way mass caused spacetime to bend and how that bending dictated motion. At times, he came close only to discover that the formulation was incomplete or inconsistent. Some versions violated conservation of energy, others contradicted observation. Some lacked the generality needed to describe all frames of reference. Each failure sharpened his understanding, but left him restless. During these years, Einstein worked with an intensity that strained even his remarkable endurance. He filled notebooks with attempts, walked for hours turning equations over in his mind, and held long conversations with colleagues about the structure of geometry. At times he doubted whether he would ever find the correct framework, yet he could feel that the solution was near. The universe behaved too consistently for its laws to remain hidden forever. Every fragment of evidence pointed in the same direction. Gravity was geometry. Time itself slowed near mass. Paths curved because space-time curved. The final breakthrough came when Einstein recognized that the key lay in connecting the curvature of space-time to the distribution of mass and energy through a specific mathematical object known as the stress-energy tensor. This tensor described the density and flow of energy in all its forms. By linking space-time curvature to this quantity, he could finally express gravity not as a force, but as a geometric response to the presence of energy. When he wrote the relationship in its complete and elegant form, he knew immediately that it captured the structure of the physical world. This equation revealed that mass and energy told spacetime how to curve, and curved spacetime told matter how to move. It was a simple sentence describing an idea of immense depth and beauty. It replaced the notion of action at a distance with a continuous interplay between geometry and matter. The universe no longer behaved like a stage governed by external pulls, but like a living fabric shaped from within. One of the first tests of this new theory came from the orbit of Mercury. When Einstein applied his equations to the Sun and calculated the motion of the innermost planet, the lingering discrepancy appeared naturally. The anomaly was not an error. It was the signature of space-time curvature near the Sun. The theory predicted the exact amount of precession that astronomers had measured. In that moment, Einstein understood that he had uncovered the true nature of gravity. With the field equations complete, the universe transformed. Space and time had become dynamic ingredients of reality. They twisted and stretched in response to energy. They shaped the motion of planets, guided the paths of light, and controlled the rhythm of clocks. Gravity was no longer a mysterious force. It was the architecture of space-time itself, a quiet but profound illusion created by the flow of time. Einstein stepped into the next phase of his work with a sense that the universe had already whispered its structure to him. The challenge now was to reveal that structure in full clarity, to transform insight into a complete theory that could describe every motion from the fall of an apple to the bending of starlight. He no longer pictured space and time as separate realms. He no longer imagined gravity as a pull. Instead, he saw a single four-dimensional continuum whose shape shifted in response to mass and energy. This vision allowed him to look at familiar phenomena with a transformed understanding. A planet did not orbit because a force dragged it. It orbited because the flow of time and the contours of space guided its path. But the beauty of the idea meant little without a mathematical language capable of describing it. Einstein had already discovered that ordinary geometry could not serve this purpose. The flat diagrams of Euclid could not capture the depths of a universe where time itself stretched and curved. He needed a framework that could describe how distance behaved in a space that was not rigid, and how paths bent in a world where straight lines were not always straight. The mathematics of Bernhard Riemann offered exactly this, providing a way to describe curved surfaces and higher dimensional shapes with precision. Riemann had shown that a surface could possess its own internal geometry, independent of whatever space it seemed to occupy. A sphere, for example, displayed angles and distances that differed from those on a plane. A triangle drawn on a sphere could have angles that summed to more than 180 degrees. These properties emerged not from forces, but from curvature itself. Einstein realized that this same reasoning could be applied to the universe. If mass curved space-time, then objects moving within that curvature would follow paths determined by the geometry, not by an external pull. He began using the mathematical tools developed by Riemann and others who had explored the geometry of curved surfaces. They described curvature through quantities that revealed how distances changed from point to point. These ideas felt foreign at first, heavy with symbols and unfamiliar structures. But Einstein persisted, knowing that he was not merely manipulating equations, but uncovering the architecture of reality. Geometry was no longer a descriptive tool. It had become the very essence of gravity. To build his theory, he needed an equation that linked the curvature of space-time to the mass and energy it contained. He understood that matter could not simply sit in space without influencing it. The presence of a star or planet must alter the rhythm of time nearby. Clocks would tick at different rates depending on the depth of the gravitational potential. This difference in the flow of time would bend the paths of objects naturally. In this way, the equations describing time dilation and those describing spatial curvature were not separate. They were part of one unified geometry. Einstein explored many possible combinations of geometric quantities, searching for an equation that respected the principles of relativity and reduced to Newton's law under ordinary conditions. He needed a relationship that preserved conservation of energy and momentum. He needed one that described how space-time curved in response to all forms of energy, not just mass, but also pressure and motion. Each candidate equation carried part of the truth, yet failed in some aspect. The process was slow and often frustrating, but he sensed that nature operated according to a pattern elegant enough to reveal itself if approached with patience. As the geometry took shape, Einstein began to grasp its implications in deeper ways. In flat spacetime, the straightest path between 2 points was a straight line. In curved spacetime, the straightest path was a geodesic, a path determined entirely by the geometry. Objects in freefall simply followed these geodesics. They felt weightless because nothing acted upon them. Gravity became not a force, but the natural motion of objects through warped space-time. This insight linked the everyday experience of falling to the deepest structure of the cosmos. Einstein imagined light passing near a star. In Newtonian physics, light had no mass and therefore no reason to bend. But if space-time curved near the star, then light would follow that curvature, just as planets followed theirs. The bending of starlight became not an anomaly, but a direct consequence of geometry. Time itself slowed near the star, and since light always moved at the same speed, it naturally shifted its path through regions where time flowed differently. What seemed mysterious under the classical framework became inevitable under the geometric one. The beauty of the emerging theory strengthened Einstein's resolve. He saw that the mathematics could describe not only planets and light, but any situation where mass and energy influenced the structure of spacetime. The universe behaved like a vast fabric that stretched and compressed according to the energy within it. Every motion, every orbit, every shift in time resulted from the shape of that fabric. Einstein pressed on, knowing he was approaching the moment where all the pieces would align. The field equations that described how matter curved spacetime were close, waiting for the final insight that would bring the theory into its complete and elegant form. The transformation was almost ready to enter the world. The idea that gravity was a force would soon fade, replaced by a vision far more sweeping and profound. Einstein moved deeper into the geometric heart of his theory, guided by an intuition that geometry alone could explain every gravitational phenomenon ever observed. Yet the mathematics remained a maze of symbols, tensors, and relationships that twisted through multiple dimensions. To navigate this landscape, he leaned heavily on the work of Marcel Grossman, whose knowledge of advanced geometry provided the structure Einstein needed to express his ideas. Together, they explored formulations that could describe how spacetime itself responded to energy. Each attempt expanded Einstein's understanding, even when it failed to produce the complete picture. He recognized that nature demanded a theory that treated all observers equally. No preferred frame could exist in a universe shaped by relativity. The laws of physics had to remain the same for anyone moving at constant speed or even accelerating. Gravity could not be a special force requiring exceptions. It had to emerge naturally from the structure of spacetime in a way that remained consistent across all perspectives. This requirement placed tight constraints on any possible equation. It forced Einstein to consider how every piece of geometry fit together under changes in motion. The mathematics of general covariance, which allowed equations to hold under any coordinate transformation, became his guiding principle. As Einstein applied these ideas to physical situations, he began to see how deeply mass and energy influenced the flow of time. A clock held near a massive object would tick more slowly than a clock far away. This effect was not a trick of perspective, but a real physical change in the passage of time. The difference was subtle for ordinary situations, yet undeniable when measured with precision. In this insight, Einstein found one of the most important keys to understanding gravity. If time itself flowed at different rates, depending on gravitational potential, then objects moving through regions where time slowed would naturally shift their paths. They would appear to accelerate toward the massive object, not because a force pulled them, but because time guided their motion inward. Einstein imagined a person standing at the edge of a large mass. The flow of time near the mass ran slightly slower than the flow of time farther away. A freely falling object would naturally move toward regions where time flowed more slowly because its path through space-time curved toward that direction. This picture explained gravity with an elegance that no classical force could match. Gravity became simply the structure of time itself, bending in response to mass. But turning this insight into a precise mathematical relationship proved difficult. Einstein tested one equation after another, checking how each one behaved under the conditions of the solar system. Some equations produced results that contradicted observation. Others violated the conservation of energy or failed to reduce to Newton's law in situations where gravity was weak. The mathematics of curvature required care. A small misstep could lead to an expression that looked correct in general form but failed when applied to specific problems. During this period, Einstein experienced moments of intense excitement, followed by heavy disappointment. He wrote papers describing early versions of the Ye theory only to retract them later when he discovered hidden inconsistencies. He returned again and again to the fundamental requirement that the geometry of spacetime had to reflect the presence of energy in a precise and consistent way. Each correction brought him closer to the truth. Each abandoned equation revealed another clue about the structure he sought. Einstein found himself thinking constantly about how matter shaped geometry. He imagined stars bending the space-time around them, creating wells of curvature that guided the motion of planets. He imagined how pressure and energy inside a star could influence not only its physical structure, but the very shape of the space-time surrounding it. He began to understand that gravity could not be described by mass alone. Energy in all its forms, including pressure and motion, contributed to the curvature. This insight widened the scope of the theory and revealed the full power of the geometric approach. As Einstein refined the mathematics, he revisited the motion of Mercury. The planet had puzzled astronomers for decades with its small but persistent anomaly. Classical gravity could not explain this shift in its orbit. Yet when Einstein applied his evolving equations, the discrepancy began to dissolve. The curved geometry near the Sun naturally produced the additional precession that astronomers had measured. The orbit no longer required unseen planets or ad hoc corrections. It emerged directly from the structure of space-time itself. Encouraged, Einstein pushed further. He tested the bending of light near the Sun, an effect Newtonian physics could not capture. If space-time curved near the Sun, then light passing by would follow that curvature. His equations predicted a specific amount of bending. This prediction would soon become a critical test of the new theory. But even before the test was performed, Einstein felt the unmistakable sense that the universe had finally revealed the form of its gravitational law. His work was close to completion. The geometry of space-time, the influence of mass and energy, the behavior of time itself, all converged into a single structure. What remained was to express it in one final elegant relationship linking curvature to energy. The pieces were assembled. The pattern was clear. One more step would complete the journey. Einstein pushed into the final stretch of his search with a mixture of exhaustion and exhilaration. Years of wrestling with equations had sharpened his insight. The pieces of the puzzle no longer drifted in isolation. They had begun to lock together into a single coherent design. He sensed that the universe was only one step away from revealing its full geometric law, a law that would describe how matter shaped space-time and how space-time guided motion. Yet that final step demanded absolute precision. The equation he sought had to be both beautiful and exact. It needed to express the curvature of space-time in a form that respected every symmetry of nature and every constraint of physical law. Einstein studied the relationship between curvature and energy through the lens of the geometry developed by Riemann and further refined by Ricci and Levi-Civita. These mathematicians had created a way to describe curvature using quantities that captured how vectors changed as they moved through space. The curvature of a surface or a space could be expressed through a geometric object that encoded how nearby paths diverged or converged. Einstein realized that this object, the curvature tensor, held the key to describing gravity. If mass and energy bent space-time, then the curvature tensor must reflect that bending. The challenge was linking it to the physical content of the universe, expressed through the stress-energy tensor. He needed an equation that balanced these two entities. One side would describe the curvature of space-time. The other side would describe the distribution of energy and momentum. The relationship had to hold in every region of the universe, whether near a massive star or in the nearly empty expanse of interstellar space. It needed to preserve conservation laws and remain consistent under any change of coordinates. These requirements tightened like threads around a single, unique structure. The more Einstein tested possible forms, the more the correct one began to stand out from the rest. Then, in a moment of clarity born from years of struggle, Einstein wrote the equation that captured everything. It was a relationship that linked the curvature of space-time directly to the stress energy within it. When he placed the final terms together, he recognized instantly that it held the shape of truth. The equation described how matter told space-time how to curve. It described how curved space-time told matter how to move. It encompassed Newton's law as a natural limit in weak gravitational fields. It satisfied the principles of relativity. It preserved conservation of energy. and it provided, without adjustment, the exact correction needed to explain Mercury's orbit. Einstein felt a surge of certainty so powerful that he famously said he would have been surprised if the theory had been wrong. To him, the equation did not feel invented. It felt discovered, as though it had always been waiting in the structure of the universe, hidden behind centuries of classical assumptions. He applied the new equation to the motion of planets and found that their paths emerged naturally from the curvature around the Sun. He calculated the bending of light near a massive object and found a prediction twice as large as the value suggested by Newtonian interpretations. He examined how time flowed near a massive body and saw that clocks slowed according to the geometry. Every consequence of the equation aligned with the experimental clues that had been accumulating for decades. Even more astonishing was the realization that the geometry could describe extreme situations Newtonian physics had never imagined. It predicted the possibility of regions where curvature became so strong that not even light could escape, a possibility that would later be understood as a black hole. It described how time and space intertwined in the presence of mass, and it revealed that the universe itself could expand or contract depending on the distribution of energy, a discovery the world would later confirm. Einstein stepped back from the final equation and felt the weight of centuries shift. Gravity had transformed from a force into geometry. Motion had transformed from the response to a pull into the natural path through a curved spacetime. The universe had revealed itself not as a machine bound by invisible tethers, but as a vast and dynamic fabric, whose shape determined every movement within it. The stage was no longer rigid. It curved and twisted. It breathed with the presence of matter. Time itself flowed differently from place to place. The fall of an apple, the orbit of a planet, the bending of starlight, all became expressions of the same underlying principle. The world was now ready for the first empirical test, a test that would take place far from laboratories, under the shadow of an eclipse, as starlight brushed past the curved geometry near the Sun. The moment had arrived for the universe to answer. Einstein had reshaped gravity into geometry with a theory that felt both inevitable and astonishing. But no idea in physics becomes truth until nature agrees. The equations were elegant, the logic was sound, and the explanation for Mercury's orbit matched perfectly. Yet the world would not accept a rewrite of gravity without the clear voice of observation. The stage for that confirmation would not be a laboratory filled with instruments, but the open sky during a rare moment when the Sun dimmed its brilliance just enough for starlight to reveal its path. The prediction was simple in concept, yet profound in meaning. Light passing near the Sun should follow the curvature of space-time, bending slightly inward as it glided across the distorted geometry. The effect was small, but Einstein's equations provided a precise value. If astronomers could measure the position of stars near the edge of the dimmed Sun during a total solar eclipse, then compare those positions to their normal locations in the night sky, they would see the shift caused by space-time curvature. This measurement would reflect not a pull on the light, but the shape of time and space themselves. In the year 1919, the world waited as expeditions traveled to remote regions where a total eclipse would darken the sky long enough to perform the test. Telescopes were positioned, photographic plates were prepared, and as the moon drifted across the Sun, the hidden stars revealed themselves for a brief moment. When the plates returned to England and were examined with meticulous care, the results confirmed Einstein's prediction. The starlight had shifted by the exact amount required by the curvature of space-time near the Sun. The announcement rippled through the world, transforming Einstein from an obscure thinker into one of the most recognized figures in history. But beyond the headlines and excitement, the importance of the result lay in what it revealed. Gravity was not a force in the classical sense. It was the geometry of the universe made visible through the behavior of light. For the first time, humanity had observed the bending of space-time itself. Einstein already understood that starlight was only the beginning. His equations predicted other effects that could be measured with growing precision. One of the most stubborn mysteries of 19th century astronomy the perihelion precession of Mercury, now stood illuminated by the geometric theory. Newton's law explained almost all of Mercury's motion, but a small remainder had resisted explanation. Einstein's equations matched that remainder exactly, not by correction or adjustment, but by revealing that the curvature of space-time near the Sun naturally produced the additional shift. The mystery dissolved not because someone forced the equations to fit the data, but because the truth had finally been revealed. Einstein also predicted that time itself flowed differently in the presence of gravity. A clock placed near a massive object would tick more slowly than a clock positioned farther away. This idea, though subtle, was one of the most powerful implications of general relativity. It explained gravity not as a downward pull, but as the result of time running at different rates in different locations. For years, the effect remained too small to measure directly. But as technology advanced, experiments began to reach the necessary precision. In the late 1950s and early 1960s, physicists Robert Pound and Glenn Rebka used gamma rays inside a tall tower to measure the slight change in frequency caused by gravitational redshift. Light climbing in a gravitational field lost energy exactly as Einstein's equations predicted. The measurement was delicate, requiring extraordinary care, yet it confirmed one of the most fundamental aspects of general relativity. Gravity affected not only the paths of objects, but the rhythm of time itself. As clocks improved, the experiments grew even more striking. In the early 1970s, scientists placed highly accurate atomic clocks aboard airplanes and flew them around the world. When the clocks returned, they disagreed with identical clocks that had remained stationary. The difference matched the predictions of relativity. Earth's rotation, motion, and gravitational field had altered the flow of time along each airplane's path. Time dilation was no longer a concept hidden in equations. It had become a measurable reality. With every test, the geometric nature of gravity became clearer. Spacetime shaped the motion of planets. It curved the path of light. It altered the rhythm of clocks. These effects did not require speculation or philosophical interpretation. They emerged directly from observation. Even radio waves sent across the solar system revealed the structure of space-time. When signals passed near the Sun on their way to distant probes, they slowed slightly because they traveled through deeper gravitational potential. This delay, measured with remarkable precision, matched Einstein's predictions perfectly. The effect became known as the Shapiro delay, another demonstration that the universe honored the geometry described by general relativity. Each experiment strengthened the same conclusion. Gravity was not a force reaching across space. It was the architecture of spacetime itself. The bending of time and the shaping of space guided everything from the slow drift of planets to the flight of photons racing across the cosmos. The scientific world no longer doubted the geometric nature of gravity, yet the deepest tests still awaited discovery. Beyond the gentle curvature that shaped planetary orbits, beyond the subtle time shifts felt by clocks, lay a realm where spacetime twisted with unimaginable intensity. To explore that realm, the next chapter would turn toward the darkest, most extreme predictions of Einstein's theory. The confirmation of starlight bending and the triumphs of early clock experiments energized the scientific community. Yet Einstein knew that these were only the first steps in revealing the full depth of curved spacetime. His equations had opened a doorway into a universe far stranger and more dynamic than the gentle arenas of planetary motion. Hidden within the mathematics were predictions that stretched far beyond the familiar. Some predictions described conditions so extreme that no one in Einstein's time could imagine observing them directly. Still, the theory insisted they were real. And slowly, through decades of technological progress, nature began revealing them one by one. Astronomers turned their attention to places where gravity pressed against its own limits. Dense stars, remnants of earlier cosmic generations, crowded matter into volumes so small that the curvature of space-time grew intense. These objects did not behave like ordinary stars. Some of them emitted powerful bursts of radiation as gas spiraled inward along steep gravitational contours. Telescopes detected bright sources of X-rays far beyond the level that ordinary stars could produce. At first, these sources puzzled observers, but as data accumulated, a pattern emerged. The emissions came from systems where an unseen companion object exerted an extraordinary pull, drawing matter off a nearby star. This siphoned gas heated as it fell inward, glowing in high-energy light before disappearing beyond view. Einstein's equations offered a natural explanation. The invisible companion was not a normal star at all, but a collapsed object where space-time curved so violently that light itself could not escape. These systems provided the first indirect evidence for what would eventually be known as a black hole. The idea sounded like science fiction, yet it rose directly from Einstein's geometry. If enough mass were compressed into a small enough region, space-time would pinch inward so steeply that all paths would lead inward. Even light, always racing through the universe at its highest possible speed, would find no route outward. The structure of space-time itself sealed the region off from escape. The term black hole would not appear until later, but its existence was already encoded in the equations of general relativity. Even stronger evidence came from the center of our own galaxy. Astronomers observe stars moving in tight curves around an invisible point, their speeds far too high to be explained by ordinary matter. Year after year, these stars traced orbits that revealed the presence of an immense gravitational influence concentrated in a region too small to see. The mass required to guide their motion equaled millions of suns, yet no light emerged from that central location. The only explanation consistent with Einstein's theory was a supermassive black hole. The geometry of space-time at the galactic center had become so steep that no light escaped its grasp. The stars responded not to a hidden surface or a sphere, but to the shape of space-time around a point of extreme curvature. These discoveries deepened confidence in general relativity, not only because the data matched predictions, but because the theory offered no alternative. In the Newtonian view, such concentrations of mass would collapse infinitely under their own pull without any clear physical meaning. In the geometric view, however, collapse produced a region where curvature intensified until it formed a boundary known as an event horizon. This boundary marked the place where all directions pointed inward. It was not a wall, but a geometric threshold where space and time had reshaped themselves so completely that escape became impossible. As instruments improved, astronomers began to see increasingly detailed signatures of this extreme gravity. Gas whirling near a black hole emitted radiation with patterns determined by the stretching of time. Clocks ran more slowly near the boundary, altering the rhythm of the emissions. Light escaping outward shifted to longer wavelengths because it climbed from deep gravitational potential. These effects, predicted by Einstein decades earlier, appeared in measurements with growing clarity. Each observation served as a reminder that space-time was not an abstract construction. It was a physical fabric with measurable properties, one that bent and twisted according to the energy it enclosed. Then, in the second decade of the 21st century, a new achievement brought the geometry of black holes into view. A global network of radio telescopes formed an Earth-sized instrument capable of resolving structures smaller than anything previously imagined. By synchronizing distant observatories with astonishing precision, scientists captured an image of the shadow cast by a black hole at the center of a nearby galaxy. The result revealed a circular darkness surrounded by glowing gas, the outline shaped not by a surface, but by the path of light around a region of extreme curvature. It was the first visual confirmation of an object predicted purely from the equations of general relativity. With each discovery, from X-ray binaries to the orbits of stars to the captured image of a black hole shadow, the universe spoke with growing clarity. Gravity was not a simple force. It was a manifestation of geometry. The bending of space-time became fully visible in the motions of matter, the stretching of time, and the behavior of light near the steepest gravitational wells known. Yet even these spectacular confirmations marked only the beginning. Einstein's theory predicted not only curved spacetime, but ripples traveling through that curvature, vibrations produced when massive objects collided or shifted violently. These ripples, called gravitational waves, would be even harder to detect. They would require instruments sensitive enough to measure distortions so small they seemed beyond imagination. Einstein's equations carried within them a quiet but astonishing prediction, one that remained invisible to the scientific world for decades simply because no instrument was sensitive enough to detect it. If space-time was a fabric capable of bending, then it should also be capable of vibrating. When massive objects moved or collided, they should send ripples outward through the geometry, stretching and compressing distances as they traveled. These ripples would be unimaginably faint by the time they reached Earth, but their existence followed directly from the structure of general relativity. They were not optional. They were a natural consequence of a universe made of geometry. Einstein recognized this implication in the early years after he completed his theory. Yet even he doubted that such waves could ever be observed. The distortions would be so small that even the most sensitive instruments of his era could not hope to detect them. A passing gravitational wave might stretch a length of several kilometers by less than the width of a single atomic nucleus. Such a measurement lay far beyond the reach of 20th century technology. For decades, the waves remained a theoretical prediction, acknowledged but silent. As the century progressed, astrophysicists realized that there were events in the universe energetic enough to produce strong gravitational waves. Binary stars orbiting each other would radiate small waves as they gradually spiraled inward. The collapse of a massive star would produce a sharp outburst. The merging of two dense remnants, such as neutron stars or black holes, would create the strongest waves of all, sending disturbances across billions of kilometers. If these waves reached Earth, they would carry direct information about the most violent regions of space-time. The first indirect clues emerged from the careful study of a pair of neutron stars discovered in the 1970s. These dense remnants orbited each other in a tight and rapid dance. Over time, their orbits slowly shrank, just as general relativity predicted for a system radiating gravitational energy. When astronomers measured this decay with extraordinary precision, they found the match to Einstein's predictions so perfect that no alternative explanation remained. The system behaved as though it were losing energy exactly at the rate required by gravitational wave emission. This discovery earned the Nobel Prize and offered the first clear sign that gravitational waves were real, even though none had yet been detected directly. Still, the field demanded more. A direct observation would allow scientists to listen to the universe in a new way. It would provide not only confirmation of the theory, but a window into phenomena previously hidden. The challenge was building an instrument capable of measuring distortions so small they seemed impossible to conceive. Researchers imagined a device where long arms would form a giant L-shaped structure. Laser beams would travel up and down each arm, reflecting off mirrors suspended in vacuum. If a gravitational wave passed through, it would stretch one arm slightly while compressing the other. The tiny difference in the travel time of the laser beams would reveal the presence of the wave. This idea eventually became the foundation of an observatory known as the Laser Interferometer Gravitational Wave Observatory, or LIGO. Construction required breakthroughs in lasers, vacuum systems, vibration control, and mirror technology. Every part of the instrument needed to be isolated from disturbances smaller than anything previously measured. Researchers spent decades refining the design, knowing that even the faintest background noise could conceal the signal they sought. The observatory stretched for kilometers across isolated landscapes, ready to detect distortions 1,000 times smaller than a single proton. For years, the detectors listened to the silence of space-time. Engineers improved their sensitivity, upgraded their components, and pushed their technology closer to the theoretical limits. Then, one morning in the year 2015, As the upgraded observatory began its new run, a signal passed through the detectors. It lasted only a fraction of a second, a faint chirp-like pattern rising in pitch as two massive black holes spiraled together and merged. The wavefront had traveled more than 1 billion years through the universe before gently brushing Earth. The pattern matched perfectly the prediction of general relativity for the collision of two black holes. The achievement marked one of the greatest scientific milestones in history. Humanity had heard spacetime speak for the first time. The ripples Einstein predicted a century earlier had revealed themselves in tones carried across cosmic distances. The discovery confirmed not only the existence of gravitational waves, but also the existence of binary black holes, objects so extreme that they had previously been known only through indirect evidence. In the years that followed, the observatory detected many more signals, including the merger of neutron stars. That event produced both gravitational waves and a burst of light visible across the spectrum, allowing astronomers to observe the same cosmic collision through two different channels. This moment marked the birth of multi-messenger astronomy, a field where the geometry of spacetime and the glow of matter combine to reveal the full story of cosmic events. Each detection strengthened the same conclusion. Spacetime was not a silent stage. It flexed and vibrated with the motion of massive objects. It carried information across the cosmos in the form of gentle distortions. And it responded to the dance of stars and black holes exactly as Einstein's equations required. With gravitational waves now directly observed, every level of Einstein's theory had been validated. Light bent where geometry curved. Time slowed where gravity deepened. Planets followed geodesics shaped by spacetime. Black holes revealed the steepest contours of curvature. And the universe itself resonated with waves traveling through the very fabric of reality. The next chapter would explore these extreme environments further, revealing how spacetime behaves when it reaches the limits of what nature allows. The discovery of gravitational waves opened a new sense for listening to the universe, yet the signals that reached Earth told only part of the story. Einstein's equations contained predictions far more extreme than gentle distortions or subtle time shifts. They described places where spacetime curved so violently that familiar intuition collapsed. These places were not exotic in the sense of imagination, but inevitable in the mathematics. If enough mass were packed into a small enough region, the geometry would fold inward until every possible path pointed the same way. Not outward, not sideways, only inward. Such a region would not simply trap matter, it would trap light itself. This prediction seemed almost impossible to believe when it first emerged from the equations, yet nothing in the mathematics allowed it to be avoided. The curved universe Einstein described contained the seeds of these regions from the moment the theory was born. To understand how such an object could exist, imagine a star many times more massive than our Sun reaching the end of its life. When the nuclear reactions in its core fade, nothing remains to resist the inward pull created by its own mass. The outer layers collapse, the core shrinks, pressure rises beyond imagination. If the mass is great enough, the collapse does not stop. It continues until the geometry of spacetime bends inward so steeply that no outward path remains. The result is a black hole, a region defined not by matter or surface, but by a boundary called the event horizon. This boundary is not a physical surface. It is a point of no return, a place where the flow of spacetime carries everything inward. Einstein's equations describe the geometry around such an object with remarkable clarity. Far from the collapsed star, spacetime behaves almost normally. Clocks tick at nearly familiar rates. Light travels in nearly straight lines. But as one approaches the event horizon, time begins to stretch. A clock near the boundary runs more slowly compared with a clock far away. Light struggles to climb the steep curvature, losing energy and shifting to longer wavelengths. Space itself becomes so distorted that directions lose their familiar meaning. The radial direction draws everything inward. not because of a pull, but because space-time itself is shaped that way. For decades, these predictions remained beyond direct observation. Telescopes could see stars moving strangely around invisible points. They could detect bursts of X-rays as matter spiraled inward towards something unseen. These signatures hinted at black holes, but could not yet reveal their full geometry. Still, the evidence grew steadily. Observers noticed that some regions of the sky produced pulses of radiation with intensities impossible for ordinary stars. They watched gas swirl around invisible centers at speeds that approached the speed of light. They measured the orbits of stars near the core of our galaxy and discovered motions so rapid and so tightly curved that only a massive compact object could explain them. The mass at the galactic center equaled millions of suns, yet nothing shone there. No surface reflected light. No star revealed itself. The only explanation consistent with general relativity was a supermassive black hole. As technology advanced, astronomy entered a new era where extreme curvature could be studied more directly. Instruments detected how time slowed near a black hole by examining the rhythm of light emitted by gas in its grip. They watched radiation shift to lower frequencies as photons climbed from regions where spacetime was deeply curved. These changes were not guessed or interpreted loosely. They matched the predictions of Einstein's equations with astonishing precision. Still, the most striking confirmation awaited a new generation of telescopes. A global array of radio observatories linked together with exquisite timing created a virtual telescope the size of Earth. This instrument, known today as the Event Horizon Telescope, achieved the sharpness needed to observe the region just outside a black hole's event horizon. When the first image emerged, it showed a dark circular shadow surrounded by a glowing ring of superheated gas. The darkness at the center was not a physical surface. It was the region where light paths bent inward so strongly that none reached Earth. The glowing ring traced the point where space-time curved the light from behind the black hole into view. The entire image was shaped not by matter, but by geometry. This observation confirmed more than the existence of black holes. It revealed the structure of curved space-time itself, made visible through the behavior of light, trapped near the steepest wells gravity could create. The shadow matched the predictions of general relativity. The ring displayed the distortions encoded in Einstein's equations. The image was not only a photograph of an object, it was a photograph of curved geometry. Yet even these dramatic confirmations represented only the beginning. Black holes were not just massive collapsed stars. They were the deepest laboratories for understanding gravity, places where the flow of time slowed almost to a halt and where space-time revealed its sharpest edges. To explore them further, scientists turned their attention to the dynamics of matter spiraling near the horizon, the echoes of space-time vibrations after collisions, and the ways in which extreme curvature shaped everything falling toward it. The region surrounding a black hole is unlike any other environment in the universe. Here, space-time reveals its most dramatic contours, and every motion reflects the influence of curvature rather than force. Matter drawn toward a black hole does not fall in the classical sense. It follows the natural flow of space-time itself. If a black hole could be seen with complete clarity, no tether or grasping pull would appear. Instead, there would be only the quiet but relentless guidance of geometry. Everything moves inward because every possible future, every direction that time can point, aims toward the center. Gas drawn from a nearby star often forms a swirling disk around a black hole, heating as it descends the curved slope of space-time. The motion within these disks provides some of the clearest evidence that Einstein's theory mirrors reality with extraordinary accuracy. As the gas moves closer to the event horizon, it orbits faster and faster. The light it emits becomes stretched and distorted. One side of the disk appears brighter because the rotation pushes the light toward the observer. The opposite side appears dimmer because the rotation pushes the light away. These asymmetries match precisely the patterns expected from relativity. They arise not from turbulence or chaos, but from the way motion and light, behave in a curved space-time. The heat of the disk reaches astonishing levels. Friction within the whirling gas generates X-rays so intense that telescopes orbiting Earth can detect them from across the galaxy. Sometimes, the disk becomes unstable and releases sudden bursts of radiation. These outbursts reflect the shifting balance between gravitational curvature and magnetic fields within the disk. The behavior is complex but not mysterious. Every pattern in the radiation emerges from the same rules that guide all motion in the curved geometry. Observing these emissions allows astronomers to examine the structure of spacetime near the event horizon, where the flow of time slows and distances twist. Farther from the horizon but still within the reach of strong curvature, matter often forms jets that shoot outward along narrow beams. These jets can stretch across vast distances, powered by the rotation of the black hole and the magnetic fields threading the surrounding disk. Their formation involves interactions between matter, energy, and spacetime that push the limits of current understanding. Even so, their structure echoes the geometry predicted by relativity. Jets emerge along the axis of rotation because spacetime is dragged around a spinning black hole. This dragging, called frame dragging, shifts the very direction of spacetime. The jets align with this direction because it provides the path of least resistance through the curved geometry. The most compelling evidence for black holes, however, comes from the motion of stars that orbit them. In the center of our galaxy, dozens of stars trace paths tightly curved around an invisible mass, millions of times greater than our Sun. These stars move with tremendous speed, completing their orbits in years rather than centuries. Their trajectories can be measured with exquisite accuracy. When astronomers plot these motions, they find that the orbits follow the geodesics of spacetime around a supermassive black hole. Each star reveals the same story. The curvature is too steep, too concentrated, and too unyielding to be caused by any cluster of ordinary stars. Only a black hole can create such a geometry. Time behaves strangely in this environment. A clock falling toward a black hole slows compared with one far away. The slowing becomes more extreme near the horizon. For an outside observer, the clock appears to freeze at the boundary, its final moments stretched endlessly. But for the clock itself, time flows normally. This difference reflects not illusion, but the true nature of curved spacetime. Each observer experiences time according to the geometry of their path. Near a black hole, the geometry shifts so sharply that the flow of time becomes dramatically uneven. Light behaves just as strangely. If a photon climbs from near the event horizon to a distant observer, it loses energy. Its wavelength stretches, shifting the light toward red. This gravitational redshift is one of the most direct demonstrations that time itself changes near mass. The photon does not emerge weaker because it passed through a physical substance. It emerges weaker because it escaped from a region where time flowed more slowly. The precision of these predictions and the clarity of the observations leave no room for doubt. Einstein's description of gravity as curved spacetime is not a metaphor, but a physical reality. Black holes provide the clearest view of that reality because they expose geometry at its most extreme. The curves and flows that shape their surroundings are not theoretical constructs. They are measurable, observable, and consistent across every form of evidence. As scientists probe deeper into the behavior of black holes, they discovered that even the merging of these massive objects left traces in space-time. When two black holes spiral together, they send out waves that ripple through the universe. These waves, detected by observatories on Earth, carry signatures of the curvatures involved. Their shapes reveal the masses, spins, and distances of the colliding black holes. They allow researchers to test the limits of general relativity in places where space-time twists with staggering intensity. Every observation reinforces the same message. Black holes are not singular anomalies, but natural consequences of a universe governed by geometry. They represent the ultimate expression of curved spacetime, the places where the shape of the universe folds inward so completely that escape becomes impossible. And yet they are not the end of Einstein's story. The universe holds regions where curvature speaks in different ways, through vibrations that travel across cosmic distances and reveal motions long hidden from view. Einstein's equations did not stop at predicting the existence of black holes or the slow dance of matter spiraling around them. Embedded in the mathematics was the promise that events near black holes would speak across the universe in a language made not of light or particles, but of geometry itself. When two black holes approached one another, their motion stirred space-time like two stones churning the surface of a pond. As they spiraled inward, they lost energy through ripples that flowed outward at the speed of light. These ripples carried the imprint of the orbit, shrinking as the black holes drew closer, rising in frequency as the final moments approached, and then fading as the two objects merged into a single remnant. For decades, physicists studied the details of these predictions, calculating the shapes of the waves through numerical simulations and seeking their signatures in distant astronomical behavior. Yet the signals remained far too faint for the instruments of the early 20th century to detect. The universe, however, had already written the script for this drama. Long before humans built detectors, collisions of massive black holes were sending waves outward across unimaginable distances. These ripples stretched and compressed space-time everywhere they passed. They altered distances across the universe by the tiniest amounts, so small that nothing on Earth could sense them except the most refined instruments ever built. When observatories finally achieved the required precision, the universe revealed that these waves were abundant. Each detection carried detailed information about the curvatures involved. They told researchers the masses of the black holes, the speeds of their rotation, and the moment when the final union took place. Space-time had become a messenger, carrying truths from realms beyond the reach of light. These collisions also exposed the remarkable resilience of general relativity. Even in the final moments before merging, when the black holes whipped around one another at nearly the speed of light, and their surrounding geometry twisted into shapes impossible for ordinary intuition, the waves matched Einstein's predictions with astonishing precision. Every wobble, every pulse, every rise and fall in the wave pattern agreed with the mathematics. The waves even allowed scientists to test whether space-time possessed any stiffness beyond what relativity allowed. No deviation appeared. The universe behaved exactly as the geometry required. The observation of gravitational waves provided more than confirmation of theory. It opened a new frontier for understanding black holes. Researchers began studying the ringing that followed each collision, a gently fading sequence of vibrations produced by the newly formed black hole as it settled into its final shape. This ringing resembled the sound of a struck bell, except that the bell was curved space-time itself. The frequencies of the ringing revealed the properties of the black hole with exquisite detail. By listening to these tones, scientists could determine whether the geometry matched the predictions of relativity. The agreement continued to hold. Even in these extreme environments, the universe followed the rules encoded in Einstein's equations. As gravitational wave astronomy expanded, new mysteries appeared. Some signals suggested that black holes formed from stars previously unknown. Others revealed mergers between objects that challenged earlier assumptions about how massive stars evolved. Each detection added another piece to the puzzle of how matter moved through the cosmos, but each one also strengthened the underlying geometric framework. Nothing contradicted the idea that gravity was curvature, and that curvature shaped every path. Beyond the drama of collisions, black holes influence their surroundings through more gentle means as well. The stretching of time near a black hole created observable delays in radiation, allowing astronomers to map the contours of space-time indirectly. Gas in the accretion disk flickered as it moved through regions of different curvature. By tracking these flickers and comparing their timing to the predictions of relativity, researchers traced the flow of matter down the curved slope toward the horizon. Every rhythm matched the expected pattern. Time did not flow evenly near a black hole. It stretched according to the depth of the gravitational well, exactly as Einstein had shown. In the most extreme cases, black holes became engines of cosmic transformation. The jets that emerged from their poles shot across vast distances, influencing the formation of galaxies and regulating the birth of stars. Though the processes powering the jets remained complex, the underlying geometry shaped every part of their behavior. Frame dragging, the twisting of space-time around a rotating black hole, aligned the jets with the axis of rotation. These jets revealed that even when gravity acted through interactions with magnetic fields, the foundation remained the same. Geometry guided the flow of energy. Black holes stood at the intersection of theory and observation, bridging the gap between mathematics and the cosmos. They revealed time slowed, light bent, paths twisted, and waves traveled through the universe, carrying stories of collisions beyond imagination. They were not anomalies or curiosities. They were the natural expressions of a universe built from geometry. Their existence confirmed that the idea of gravity as a force was outdated. Gravity emerged from the shape of space-time, and black holes were the clearest expression of that shape. With every test passed and every prediction confirmed, the world saw general relativity not as a clever theory, but as a precise description of reality. Yet black holes represented only one part of Einstein's vision. The universe also spoke through gentle ripples that carried information across cosmic distances. Those ripples, already discovered, hinted at an even deeper truth. The fabric of space-time did not only curve, it vibrated. And the story of those vibrations would transform our understanding of the cosmos once again. By the time black holes revealed their shadows and starlight traced the curves of space-time, one final prediction of Einstein's theory still hovered like a distant echo waiting for the right moment to be heard. The universe, he said, should vibrate. Gravity should not be silent. Whenever massive objects moved with great violence or great precision, they should send ripples outward through space-time. These ripples would travel across the cosmos at the speed of light, stretching and compressing the geometry as they passed. They would be unimaginably faint by the time they reached Earth, but they would carry with them the fingerprints of the events that produced them. They would reveal the masses, the orbits, the collisions, the very shape of the motions. They were the voice of the universe, the whisper of geometry in motion. Einstein treated the idea cautiously. He understood the prediction flowed directly from the equations, yet he doubted that such tiny disturbances could ever be caught by human hands. Space-time was stiff. To make it ripple took enormous energy. Two black holes circling one another could produce waves that shook the universe. But after crossing billions of kilometers, those waves would arrive at Earth as distortions smaller than the width of a subatomic particle. Einstein suspected that these waves would remain a mathematical curiosity, real but undetectable. It would take a century for technology to catch up. Even so, the first clues appeared earlier than anyone expected. In the 1970s, astronomers discovered a pair of neutron stars locked in a tight orbit around each other. These dense objects each contained more mass than our Sun, compressed into a sphere only about 20 kilometers wide. They orbited rapidly, completing a full circle in hours. According to general relativity, such a system should lose energy over time by radiating gravitational waves. The orbit would shrink slowly and predictably. When physicists measured this decay, they found it matched Einstein's prediction with remarkable precision. The neutron stars circled closer and closer together, exactly as the geometry required. This was not yet a direct detection of gravitational waves, but it was a clear sign. The waves were real, and they were carrying energy away, just as the equations described. To detect the waves directly, scientists needed an instrument capable of sensing distortions 1,000 times smaller than a proton. They imagined a device where two long arms formed a perfect right angle. A laser would travel down each arm, bounce off a mirror, and return to a detector. If a gravitational wave passed through, it would stretch one arm while compressing the other. The laser beams, returning slightly out of sync, would reveal the faint tremor of space-time. But building such an instrument required levels of precision and stability that had never been achieved before. Every vibration from Earth, every temperature shift, every bit of noise inside the instrument could overwhelm the signal. Despite the difficulty, the project moved forward. After decades of design, construction, and refinement, 2 observatories stood ready. They stretched across quiet rural landscapes, waiting in silence. While the world imagined peaceful stillness, those observatories listened constantly for a ripple in the architecture of existence. In the year 2015, only days after an upgraded run began, a signal appeared. It was faint, brief, unmistakable. A low tone rising swiftly in pitch, a chirp unlike any sound that fragile detectors had ever caught. It was the signature of 2 black holes spiraling together and merging into one. The wave had traveled for more than 1 billion years before brushing Earth gently enough to move the mirrors by less than a whisper of a whisper. Yet the pattern matched the predictions of general relativity perfectly. The signal contained the masses, the spins, and the final collision encoded in its shape. The universe had spoken in the language Einstein predicted a century earlier. The discovery marked the beginning of a new era. No longer confined to observing light, scientists could now observe space-time directly. Each gravitational wave detection carried information that no telescope could reveal. Some waves came from black holes far larger than those known before. Others came from smaller black holes merging in rapid spirals. And then came a signal of an entirely different kind. In the year 2017, observatories recorded the merger of 2 neutron stars. But this time, the wave was accompanied by a burst of light. Telescopes across Earth and in orbit captured the event. For the first time in history, the same cosmic collision was observed through both gravitational waves and electromagnetic radiation. This achievement opened the door to multi-messenger astronomy, a field where scientists could watch matter and geometry respond together to the same event. Gravitational waves revealed details of the collision that light alone could not provide. They revealed the masses of the stars. They revealed how quickly they orbited before merging. They revealed how the final remnant settled. Light revealed the jets of radiation and the creation of heavy elements. Together they painted a complete picture of the event. It became clear that gravitational waves were not merely curiosities. They were essential tools for understanding the deepest behaviors of matter and space-time. With each detection, the universe whispered new stories. The signals arrived from distances so vast that their origins lay in epochs older than human civilization. Each ripple carried information about regions where gravity reached extremes far beyond those found in the quiet orbit of planets. These waves confirmed that black holes could merge. They confirmed that neutron stars produced heavy elements when they collided. They confirmed that space-time behaved exactly as Einstein's theory predicted, even under extraordinary conditions. As the observatories expanded and new detectors came online in different continents, the sensitivity improved. More waves were caught. More stories arrived. Each signal strengthened the foundation of general relativity and deepened our understanding of how space-time behaved when roused by cosmic motion. But gravitational waves told more than the story of violent mergers. They revealed that the universe itself possessed a dynamic structure. They showed that space-time was not static. It was alive with motion, responding to the movements of massive objects across billions of kilometers. The universe spoke through curvature, through vibration, through the flexing of geometry itself. What these waves revealed also prepared the way for an even more profound insight. Once scientists understood that space-time could ripple, they were ready to confront a truth that general relativity made central. Gravity was fundamentally a consequence of time itself. The flow of time, not any force, governed how objects moved, and the next chapter would reveal how every fall, every orbit, and every drift in the cosmos was shaped by the simple, yet astonishing fact that time does not flow the same everywhere. From the moment Einstein completed his geometric vision of gravity, He understood that the deepest transformation lay not in the shape of space, but in the behavior of time. Space could bend and stretch, but it was time that determined how objects moved. Time was not a uniform river flowing with identical rhythm everywhere. It was a flexible current that changed speed depending on the depth of the gravitational field. This idea, subtle yet powerful, reshaped the meaning of gravity more profoundly than any curvature of space could. To understand gravity fully, one had to understand that clocks governed motion, not forces. The geometry of space-time mattered, but time itself controlled the fall. Einstein first recognized this when he imagined a person inside a freely falling elevator. Within that small cabin, the person would feel weightless. A ball released from the hand would not drop. It would hover beside the observer, drifting gently because everything inside the cabin shared the same acceleration. This simple thought experiment revealed that gravity could vanish entirely in the right frame. If gravity could disappear for someone simply by choosing a new perspective, then gravity could not be a force acting in the usual way. A force could not be removed by changing frames, but the effects of space-time curvature could. Einstein realized that the key to understanding this phenomenon lay in the flow of time. If time changed from place to place, then motion would naturally follow those changes. To see how time shaped motion, imagine two clocks placed at different heights above a massive object. The clock closer to the mass would run more slowly than the one farther away. This difference would be extremely small for everyday conditions, almost impossible to notice without precise instruments. Yet even this faint change held enormous significance. If time flowed more slowly near the mass, then the natural path of any object would tilt inward, because the geometry of space-time bent toward regions where time ran more slowly. An object in free fall did not move toward the mass because it was pulled. It moved because the fastest route through space-time, the path that minimized the time experienced by the object itself, curved toward the region where time ticked more slowly. Motion followed time. This idea could be tested even with simple experiments. If a beam of light passed near a massive object, it would bend, not because the light weighed anything, but because light always traveled along the path that took the least time. Near a mass, the flow of time slowed, and thus the shortest interval of time was found along a curved path. Light bent because time bent. Planets orbited because time flowed differently at different distances from the star. Even objects resting on the surface of Earth pressed downward, not because they were pushed, but because the ground prevented them from following their natural curved paths through space-time. Standing still required constant upward acceleration to resist the bend of time. The first direct measurement of gravitational time dilation came from the Rebka experiment in the 1950s. Researchers sent gamma rays from the bottom of a tall tower to the top. If time flowed differently at different heights, then the frequency of the radiation would shift. The shift was tiny, yet the experiment detected exactly the amount predicted by general relativity. Light climbing out of a gravitational well lost energy because the clocks at the top ran slightly faster. For the first time, humanity observed the stretching of time due to gravity, with instruments sensitive enough to detect the change. As technology improved, the truth became even clearer. In the early 1970s, scientists carried accurate atomic clocks aboard airplanes. They flew eastward around the world, then westward, then returned to compare the clocks with identical ones on the ground. The differences they found matched the predictions of relativity with astonishing precision. Gravity slowed the clocks carried at lower altitudes. Motion slowed the clocks carried at higher speeds. These experiments revealed time as a physical quantity that changed under the influence of gravity and velocity. Time was not an abstract backdrop. It was measurable and dynamic. The next major confirmation came from a system orbiting Earth that millions of people use daily without noticing its dependence on relativity. The Global Positioning System relies on satellites equipped with precise atomic clocks. These clocks orbit above much of Earth's gravitational field, Because time runs faster at higher altitude and slower for moving objects, each satellite's clock experiences two competing effects. The gravitational effect speeds the clock up relative to clocks on Earth. The motion effect slows it down. The two effects do not cancel. The gravitational effect dominates. If engineers program the satellites without correcting for relativity, the system would fail within minutes. The positions calculated on Earth would drift kilometers each day. Only by adjusting the clocks according to Einstein's predictions do the satellites remain accurate. Every navigation signal that reaches a smartphone or a ship or an aircraft carries the imprint of curved spacetime and the flow of gravitational time dilation. More recently, experiments using optical clocks have measured time dilation across differences in height, smaller than the length of a hand. A clock raised a few centimeters runs measurably faster than one placed lower. These clocks rely on atoms vibrating at frequencies of extraordinary stability. They reveal that the structure of time is so delicate, yet so responsive, that even the height of a tabletop can influence its flow. Gravity does not merely bend space, it controls time with exquisite sensitivity. This understanding transforms the meaning of motion. A falling object accelerates inward, not because something pulls it downward, but because the inward direction corresponds to regions where time runs more slowly. Motion always follows the path that maximizes the amount of time experienced by the object. In flat spacetime, this path is a straight line. In curved spacetime, it becomes a curved geodesic. The geodesic curves because time curves. The impulse to fall is the impulse to follow the natural flow of time. Every orbit, every drop, every drift reflects this truth. Gravity is the curvature of time far more than the curvature of space. The structure of time directs motion with a firmness no Newtonian force could match. Time shapes the universe from the smallest motions to the largest frameworks. And the deeper scientists explored this truth, the more clearly they saw that gravity had transformed from a force into a manifestation of space-time itself. Time revealed itself not as a passive backdrop, but as an active influence guiding the movement of every object in the cosmos. Once scientists understood that clocks ticked at different rates depending on their height in a gravitational field, they began to see gravity everywhere as a quiet expression of time distortion. Even simple experiences took on new meaning when viewed through this lens. A person standing on the surface of Earth feels weight because the ground prevents them from moving along the natural curve of time that pulls every free object downward. If the ground vanished, the person would drift along the path shaped by the flow of time, feeling no weight at all. Gravity would disappear, not because a force switched off, but because the obstruction preventing the person from following the natural curvature would be gone. This realization carried profound consequences for understanding the structure of the universe. The classical idea of a gravitational pull faded into a deeper picture. Every object in free fall followed the quickest path through space-time, the path that required the least resistance to the flow of time. In flat space-time, these paths were straight. In curved space-time, they bent smoothly. The shape of these paths depended entirely on how mass and energy slowed the passage of time in their vicinity. The bending of these paths was what humanity had always interpreted as a force. As experiments grew more precise, physicists measured the influence of time dilation in increasingly subtle environments. Satellites orbiting Earth provided some of the clearest tests. The global positioning system depended entirely on relativity, and as the atomic clocks in orbit grew more stable, researchers noticed that even minor changes in altitude and velocity produced measurable differences. Engineers had to program corrections into the satellites before launch. Without them, the system would wander away from accuracy in a matter of minutes. Time flowed more quickly where the gravitational pull weakened, and any device relying on precise timing recognized the difference immediately. Further advances in optical clocks deepened this understanding. These clocks measured time using the oscillation of electrons in atoms, producing frequencies so stable that the clocks could detect changes in gravitational potential over the distance of a few steps. A clock placed on a high platform ran measurably faster than a clock resting on the floor. This effect had nothing to do with mechanical imperfections. It arose from the structure of spacetime itself. Time ticked differently depending on height, because Earth's mass curved the flow of time. These measurements confirmed that gravity was not a force acting through space. It was a gradient of time stretching from the center of a massive object outward. Even light revealed the influence of time. Photons climbing from the surface of a planet emerged with less energy, not because anything absorbed part of their motion, but because they traveled from a region where time ran more slowly. Their climb took place through a gradient of temporal flow. The stretching of their wavelength, known as gravitational redshift, was a direct expression of time dilation. When photons fell downward, their wavelength shortened because they traveled into regions where time ran more slowly. The universe did not change the energy of light through a mechanical process. It changed it because time itself changed. Understanding time in this way also clarified why orbits existed at all. A planet circling a star followed a path shaped by the gradients of time surrounding the star. Near the star, time ran more slowly. Farther away, time ran more quickly. A stable orbit emerged when the path that maximized time balanced between these gradients. If the planet moved too slowly, it drifted inward. If it moved too quickly, it escaped the star's influence. The orbit was not a tug of war between inertia and a pulling force. It was a compromise chosen by the geometry of time. This truth extended to every scale. In galaxies, stars moved according to the time structure created by the distribution of mass. In clusters of galaxies, entire systems drifted along paths shaped by the combined curvature of countless stars and clouds of gas. Even the structure of the observable universe, the large-scale expansion of space, reflected how time moved differently in different regions. Every aspect of cosmic motion traced back to the flow of time and the curves it created. Seeing gravity as a distortion of time changed not only physics, but imagination. When people pictured objects falling, they imagined a downward pull. But in reality, those objects simply followed the path nature offered as the most efficient route through spacetime. This path curved inward because time slowed near the massive object. The shaping of time produced the motion. The motion revealed the shaping of time. Gravity became not a force, but the experience of living in a universe where time varied from place to place. This understanding prepared the way for a new frontier. Once scientists recognized that time shaped gravity and gravity shaped time, they turned their attention to places where this relationship broke down. Black holes pushed the flow of time to near stillness. The early universe compressed time and space into densities beyond comprehension. And the realm of quantum phenomena introduced questions that general relativity could not answer. The picture was extraordinary but incomplete. Time controlled motion, except in places where the classical ideas of time lost meaning. The next chapter would confront these limits, revealing where Einstein's beautiful theory succeeded and where it reached the edge of its own power. Time revealed itself as the quiet architect of motion, yet even as experiments confirmed every prediction of general relativity, physicists began to notice that this elegant framework could not stretch indefinitely. There were places in the cosmos where time behaved in ways the equations could no longer describe. These places were not merely exotic settings hidden at the edges of the universe. They appeared at the center of black holes, in the earliest moments after the universe began, and in the smallest scales where quantum effects ruled. In these realms, the smooth geometric structure of space-time fractured. The flow of time no longer followed the calm gradients predicted by relativity. Instead, it folded, compressed, or became undefined. The beauty of Einstein's theory remained intact, but its completeness drifted into question. The most striking example emerged from the heart of a black hole. Outside the event horizon, time slowed gradually. But once inside the horizon, the geometry of space-time changed so dramatically that even the concept of inside became ambiguous. Distances and directions swapped their meaning. Time pointed inward with unbreakable certainty. Every future path ended at a point where the equations of general relativity predicted infinite curvature. That point, called a singularity, did not represent a physical place in the ordinary sense. It represented the breakdown of the theory. General relativity could describe the approach to the singularity, but not the singularity itself. The mathematics lost its meaning. The curvature grew without limit, and the flow of time ceased to be something that could be measured, defined, or extended. Physicists never believed that infinities represented real features of the universe. Infinities signaled incompleteness. They suggested that another layer of physics waited beneath the surface, a deeper structure capable of describing matter and the flow of time when the densities involved reached extremes beyond classical understanding. The presence of singularities in black hole solutions made it clear that general relativity, for all its success, could not be the final word. It worked wherever space-time remained smooth. It failed where space-time tore. A similar issue appeared when scientists studied the earliest moments of the universe. Observations of distant galaxies revealed that the universe was expanding. When researchers traced this expansion back through time using Einstein's equations, they found that all matter and energy compressed into an extremely dense state in the past. The equations implied that the universe passed through a moment where density grew infinitely large. This event, like the singularity inside a black hole, represented a point where the theory offered no meaningful description. Space and time themselves began at this moment, yet the mathematics could not describe the event. General relativity was powerful, but it was not complete enough to describe the birth of space-time. The roots of the problem reached into the realm of quantum mechanics, the branch of physics that described the behavior of particles at the smallest scales. Quantum mechanics revealed that matter behaved in discrete packets. Energy existed in quanta. The positions of particles fluctuated with inherent uncertainty. None of these features appeared in general relativity, which treated space-time as a smooth geometric surface. When physicists attempted to blend the two frameworks, they discovered contradictions. The smooth geometry of general relativity clashed with the grainy unpredictability of quantum behavior. The theory that described the largest structures of the cosmos could not merge with the theory that described its smallest constituents. Over the decades, researchers proposed many approaches to reconcile these worlds. Some explored the idea that space-time might possess a discrete structure at extremely small scales. Others imagined that particles were tiny loops rather than points, with their vibrations shaping the geometry around them. Some attempted to quantize gravity by adapting the methods used successfully for other forces. Each approach offered insights, yet none produced a complete and experimentally confirmed theory. Every attempt to unify quantum mechanics and general relativity ran into profound challenges. The mathematics became difficult, predictions remained untested, and the nature of time itself seemed to change when viewed through quantum lenses. One of the most puzzling issues concerned how information behaved near black holes. General relativity predicted that anything crossing the event horizon would never return. Quantum theory insisted that information could not be destroyed. These ideas collided sharply in what became known as the information problem. Physicists debated whether information was lost, preserved, or encoded in ways that general relativity could not describe. The question revealed that the classical understanding of space-time reached a limit when confronted with quantum effects. Another challenge arose from the behavior of empty space itself. Quantum mechanics predicted that even a vacuum contained fluctuating energy. General relativity responded to energy by curving space-time. Yet when physicists calculated the curvature produced by quantum fluctuations, they found results so large that the universe would not resemble anything observed. Something in the relationship between gravity and quantum theory remained hidden, waiting for discovery. Despite these tensions, general relativity continued to succeed wherever spacetime remained smooth and curvature remained finite. It guided the motion of planets, the behavior of stars, the evolution of galaxies, and the propagation of gravitational waves. Its limitations did not undermine its correctness. They revealed that the theory, elegant as it was, described only a chapter of the larger story. The next chapter would require a new framework, one capable of blending geometry with quantum uncertainty, one capable of describing time when time itself wavered at the edges of its meaning. The recognition of these limits did not diminish the brilliance of Einstein's insight. Instead, it sharpened the sense that gravity was both understood and incomplete. Space-time curved and time-controlled motion, yet the deepest questions lay beyond reach. To move forward, scientists needed to explore new ideas while holding firmly to the evidence that had brought them this far. The next chapter would look toward the future, revealing how new instruments, new observatories, and new theories might extend Einstein's vision into realms he could never have imagined. For all its beauty and power, general relativity carried within it the seeds of its own limits. Einstein had revealed a universe where space-time curved smoothly around matter, and where time itself guided the paths of falling objects. Observations confirmed every prediction, from the slow drift of Mercury to the bending of starlight and the ringing echoes of merging black holes. Yet even as each success strengthened the theory, physicists began to see shadows gathering at its edges. These shadows did not weaken relativity. They pointed toward realms where the theory, magnificent though it was, could no longer speak the full truth. The first hints of trouble appeared in places where curvature grew too strong for the smooth fabric of spacetime to remain coherent. In the depths of a black hole, the flow of time slowed dramatically as one approached the event horizon. Inside the horizon, the geometric structure twisted even more severely. All paths aimed inward. The future pointed toward the center, and according to the equations, the curvature at the very core rose without bound. The mathematics predicted an infinite compression of space-time, a singular point where the theory itself dissolved. This infinity did not represent a physical object. It represented the breakdown of classical geometry. Relativity had carried us into a region where it could no longer describe the world. A similar failure emerged when physicists traced the expansion of the universe backward through time. Observations showed that galaxies drifted apart, that distant light arrived stretched by cosmic expansion, and that the universe once existed in a much denser state. When the equations of general relativity followed this expansion to its earliest moment, they predicted a beginning where density reached impossible levels. Time and space contracted into a state where classical geometry collapsed. The first instant of the cosmos could not be described. Relativity offered no account of how space-time began or what existed before the expansion. The theory that excelled across stars and galaxies could not reach the moment of creation. The reasons for these breakdowns did not lie in a flaw within relativity. They arose because relativity treated space-time as a continuous surface, smooth and unbroken. At ordinary scales, this picture worked perfectly. Even in the intense gravity surrounding black holes, space-time behaved with remarkable elegance. But when distances shrank to unimaginably small scales, the quantum nature of matter became impossible to ignore. Quantum mechanics governed the realm of atoms and particles, with rules that differed sharply from the smooth geometry of relativity. In the tiny scales where both theories should apply together, their descriptions collided. Quantum mechanics revealed that energy came in discrete steps. Particles behaved with inherent uncertainty. Empty space throbbed with fluctuations. None of these behaviors fit easily into the continuous geometry of relativity. When physicists tried to combine the two frameworks, the calculations refused to settle. Attempts to quantize gravity in the same way other forces were quantized produced equations that spiraled toward infinities. These infinities did not represent physical reality. They signaled that the classical picture of space-time could not continue down to arbitrarily small scales. One of the clearest signs that something deeper was missing came from the information problem associated with black holes. According to classical relativity, anything crossing the event horizon vanished from the accessible universe. The information describing the object appeared to disappear completely. But quantum mechanics insisted that information could never be destroyed. It could be scrambled or transformed, but not erased. The clash between these principles created a paradox that neither theory alone could resolve. Something in the combination of geometry and quantum theory had not yet been understood. The early universe presented another challenge. Quantum mechanics dictated that particles fluctuated constantly, even in a vacuum. These fluctuations contributed energy to spacetime. Relativity responded to energy by producing curvature. Yet when physicists calculated the curvature produced by quantum fluctuations, they found a value far larger than anything observed. If the calculations were taken literally, the universe would have curled back upon itself almost instantly. The enormous mismatch revealed a gap between the two theories. They described different aspects of nature with extraordinary precision, yet together they produced contradictions too large to ignore. These failures did not diminish the triumph of general relativity. They clarified its domain. Relativity described the universe wherever spacetime behaved smoothly. It described stars, planets, galaxies, and gravitational waves. It described the rhythms of clocks and the curves of orbits. It described the bending of light and the geometry of black holes. But it could not describe the moment where the classical idea of spacetime reached its limit. It could not describe regions where curvature soared beyond its ability to remain finite. And it could not merge with the discrete and uncertain world revealed by quantum mechanics. Physicists recognized that a deeper theory was needed, one that would contain relativity as a natural limit, but also account for the quantum structure of matter. Several approaches emerged. Some explored the idea that spacetime might be woven from tiny loops, forming a discrete structure at the smallest scales. Others imagined that the fundamental objects of nature were vibrating strings rather than point-like particles. Some tried to adapt the techniques that worked for other forces to gravity. None of these ideas were speculative in their intent. Each arose from the need to settle contradictions between measurements and equations, yet none had matured into a completed and experimentally confirmed theory. The gap between geometry and quantum behavior remained one of the deepest puzzles in physics. Still, the recognition of these limits did not dim the power of general relativity. It provided clarity wherever spacetime remained smooth and densities remained finite. It guided spacecraft with precision. It explained the structure of galaxies. It predicted the bending of time and the rippling of spacetime. And it stood firm through every test. Its limits merely pointed toward the next horizon, inviting physicists to explore the places where spacetime itself broke apart. The next chapter would look toward the future, toward the instruments humanity was building to probe the universe with sharper vision, toward the theories that aimed to extend relativity into realms where its classical form could not endure. By the time general relativity reached its centennial, it had transformed from a daring proposal into one of the most precisely tested theories in the history of science. Light bent exactly as predicted. Time slowed at the rates Einstein calculated. Black holes formed naturally from collapsing stars. Their horizons cast shadows traced by curved space-time. Gravitational waves rippled across the cosmos, carrying stories from cataclysms billions of years old. At every scale where the geometry remained smooth, the theory held with a precision that exceeded expectation. Yet humanity stood not at the end of the story, but at the threshold of a new chapter. The future of gravity lay not only in confirming Einstein's insights, but in pushing beyond them, probing the structure of spacetime with tools he could never have imagined. One of the most promising developments came in the form of space-based gravitational wave observatories. Instruments on Earth already listened to the merging of black holes with astonishing sensitivity. but they were limited by the vibrations of the planet itself. To hear the faintest and longest waves, observatories needed to operate far from Earth's disturbances. The Laser Interferometer Space Antenna, planned as a trio of spacecraft separated by millions of kilometers, would listen to deep rumbling waves produced by supermassive black holes spiraling together at the centers of distant galaxies. These waves carried information about regions so remote and so dark that no other instrument could reach them. They would reveal how galaxies grew, how black holes formed, and how space-time evolved across cosmic time. Meanwhile, pulsar timing arrays offered another way to detect long wavelength gravitational waves. Pulsars, the rapidly rotating remnants of collapsed stars, emitted beams of radiation with extraordinary regularity. Their pulses acted as natural cosmic clocks. If a gravitational wave passed between Earth and a pulsar, it would stretch or compress the distance between them, subtly shifting the timing of the pulses. By monitoring many pulsars across the sky, astronomers could detect wave patterns that extended across the galaxy. Recent observations showed clear signs of a background of slow gravitational waves, possibly produced by supermassive black holes orbiting at the centers of merging galaxies. These measurements provided yet another confirmation that space-time vibrated in ways predicted by relativity. At the same time, researchers built ever more precise atomic clocks that pushed the boundaries of time measurement. These clocks could detect changes in gravitational potential across vertical distances of only a few centimeters. Networks of such clocks, spread across Earth or sent into orbit, could map the curvature of space-time with unprecedented detail. By observing how time flowed at different locations, scientists could create real-time maps of Earth's gravitational field, measure changes caused by shifting oceans or melting ice, and study the subtle influence of tides raised by the Moon and the Sun. In the coming decades, clock networks might detect new physical effects or reveal tiny deviations from Einstein's predictions, offering clues about where the theory might eventually need refinement. Black hole imaging also continued to advance. The global network that captured the first shadow of a black hole was already expanding. Adding more telescopes increased the clarity of the images, allowing astronomers to watch the dynamics of the gas swirling around the horizon. These motions unfolded in slow waves and rapid flickers, each shaped by the curvature of space-time near the black hole. Future instruments would reveal how these structures evolved over time, how magnetic fields threaded through them, and how rotation twisted space-time itself. By observing black holes at different wavelengths and from multiple continents, scientists would build a more complete picture of the extreme geometry predicted by relativity. Other experiments set out to test the equivalence principle with even greater accuracy. The principle stated that all objects, regardless of their composition, fell the same way in a gravitational field. This idea lay at the heart of general relativity. If even the slightest deviation were found, it would signal a new layer of physics beyond the classical picture. Space agencies launched satellites equipped with delicate instruments capable of measuring tiny differences in free fall. So far, none had been detected, but each new test pushed the limits of precision. These experiments would continue, probing the principle with ever finer sensitivity, searching for signatures of new interactions or undiscovered particles. The future of gravity research also included powerful numerical simulations that allowed scientists to model the behavior of space-time in extreme environments. Computers solved Einstein's equations for situations too complex for analytical solutions, such as turbulent matter falling into black holes or gravitational waves echoing through rotating systems. These simulations matched observations with remarkable detail, offering insights into regions that could never be accessed directly. As computational power increased, researchers could explore deeper into the nonlinear structure of curvature, studying how space-time behaved when pushed to its limits. Each of these tools strengthened general relativity where it worked and helped expose the edges where it might eventually require extension. The search for a deeper theory continued, one that could merge the smooth geometry of relativity with the quantum uncertainty of matter. Whether the future belonged to ideas involving loops, strings, or entirely new frameworks remained unknown, but the search itself was guided by the same principle that shaped Einstein's work. Follow the evidence wherever it leads, trust the experiments, and allow nature to reveal its structure through observation. In this century of gravity research, the universe no longer appeared as a static space governed by distant pulls. It appeared as a dynamic fabric shaped by the rhythm of time. Clocks revealed curvature, light traced the geometry, waves carried stories from distant collisions, instruments mapped the flow of time itself. At every turn, the picture grew clearer. Gravity was not a force. It was the architecture of space-time, a geometry that guided the movement of everything from falling apples to swirling galaxies. Einstein had uncovered the illusion at the heart of gravity, revealing that what humanity experienced as a pull was the flow of time bending around mass and energy. The coming decades would deepen this insight, revealing ever more subtle details of how space-time behaved. But the core truth remained unchanged. The universe was built not from forces reaching across voids, but from the dynamic shape of space-time itself. In the end, the universe revealed a truth both simple and profound. Gravity was never a pull. It was the quiet choreography of time guiding every motion, the gentle curvature of space-time shaping every path. Einstein had peeled back the illusion and shown that the cosmos moved not because of invisible forces, but because the architecture of reality itself flowed and folded. Light bent because time slowed. Planets orbited because the geometry curved. Black holes formed because space-time could collapse under its own structure. Waves traveled across billions of kilometers because the fabric of the universe vibrated when stirred. Everywhere the same principle whispered through the cosmos. Time shapes motion. Motion reveals time. Yet even as each discovery affirmed the theory, mysteries remained at the edges. Singularities marked places where the classical picture shattered. The earliest moments of the universe hid a framework not yet understood. Quantum fluctuations hinted at an unseen layer beneath geometry. Gravity stood complete and incomplete at once, its successes undeniable, its limits unavoidable. The universe had spoken clearly, but not fully. It had revealed the curvature of space-time, the rhythm of time dilation, the dance of black holes, and the murmurs of gravitational waves. But beyond those revelations lay a deeper structure waiting in silence. Humanity now stood at the threshold of that silent frontier, listening. New observatories reached farther, new clocks measured more precisely, new theories tried to weave geometry and quantum rules into a single tapestry. The next breakthrough would not shatter Einstein's vision. It would expand it, revealing what lay beneath the smooth surface he had uncovered. Somewhere in that deeper layer, the nature of time itself waited to be understood. And so the story of gravity remained unfinished. The illusion had been revealed, but its origin had not. The universe continued to pulse with clues, faint yet persistent, as though inviting the next step. In the gentle bend of starlight, in the slow drift of galaxies, in the quiet ticking of a clock raised by a single step, the message echoed. Space-time is not a stage. It is the music, and we have only begun to hear the opening notes.